On October 21st, 2025, something had changed. Independent astronomers comparing data from live tracking with official NASA predictions noticed the impossible. DRAMASIC was not where it was supposed to be, not by a few kilometers, not by 1,000, but by more than 1 million kilometers. And the gap was widening with every passing hour. The interstellar visitor, which had dominated headlines since July, had done something that no single natural comet could do. It accelerated, pulling ahead of its predicted gravitational trajectory. 8 days later, it disappeared behind the sun, precisely as its velocity peaked, hidden from every telescope on Earth during the window. Most energy efficient for any spacecraft to make a course correction. Now, as it approaches perihelion on October 29th, the object will remain invisible, shielded by the sun's glare, doing whatever it came here to do in complete darkness. When it re-emerges in early November, we will know if that deviation was a flaw in our calculations, or if something out there just made a deliberate move. The next 2 months will either confirm we are witnessing the most unusual comet in recorded history, or prove that Avalon's warnings of extraterrestrial technology were not speculation at all. If you are as captivated and by what's unfolding up there as I am, please hit the like and subscribe button so you don't miss what happens next. And please leave a comment, letting me know where you're listening from, what time it is there, and whether you think we are looking at a comet, or something far more deliberate. And if you want to help this community grow, share this video and press the new hype button below. Thank you so much for your support. Orbital anomaly. Claims of active maneuvering. The initial data came in quietly. October 21st, 2025, 2 minutes past midnight. Coordinated Universal Time. A handful of independent trackers, running routine sky surveys, noticed something strange. When cross-referencing their observations with the Jet Propulsion Laboratory's Horizons system, JPL-BA-IATLAS, the interstellar object, had been behaving relatively predictably since its discovery in July. It had drifted off course. This wasn't the subtle drift you might expect from a measurement error. It or outgassing pressure, this was different. The object appeared ahead of where gravity alone should have placed it. To put that into context, when you track any celestial body, whether it's a satellite, an asteroid, or a comet, you are essentially watching the invisible hand of gravity guide it through space. The JPL Horizons system is one of the most sophisticated astronomical tools we have. It calculates where objects are supposed to be, based on the gravitational pull from the sun, the planets, and even the subtle tug from the mass of Jupiter, millions of kilometers away. These predictions are extraordinarily precise. When our Mars rovers land, when spacecraft perform flybys, when we track near-Earth asteroids, Horizons tells us where to look, within a margin, and of error measured in meters, not kilometers. And on that October morning, the Horizons prediction for BA-IATLAS was a right ascension of 13 hours, 46 minutes, and 57.51 seconds, a declination of 8 degrees, 15 minutes, and 20.0 arc seconds. That is where NASA said the object would appear in the sky, but the observational data told a different story. Multiple independent tracking sites, cross-referencing their measurements, found the object at a right ascension of 13 hours, 47 minutes, and 54.3 seconds, with a declination of 8 degrees and 21 minutes. For those unfamiliar with astronomical coordinates, let me explain. That is not a small discrepancy. At the distance BA-ATLAS was traveling, about 2.38 astronomical units from Earth, that angular deviation, translates to about 1.1 million kilometers of lateral displacement. Now, this is where it gets truly strange. When tracking systems show a mismatch between prediction and observation, the error usually appears in a specific direction. If your orbital data is out of date, the object appears behind where you expect it. Think about it. It's like trying to hit a moving target with old information. You always shoot where it was, not where it is. Orbital mechanics has predictable models. Comets accelerate as they approach the sun, and decelerate as they move away. Outgassing can create small, non-gravitational forces. Small jets of vapor push the object slightly off course. All of this is well understood. It's been documented in thousands of comet observations spanning decades. But DRAMASIC appeared ahead, and of its predicted gravitational position, not behind, but ahead. That completely breaks the conventional model. When an object appears ahead of gravitational predictions, it suggests something is pushing it forward, adding energy to its motion. For a comet, and that would require asymmetrical outgassing, aimed in precisely the right direction to accelerate the object along its orbit. Possible. Sure, comets can be unpredictable, but the timing here raises more difficult questions. The first group to announce the deviation. It was a group called Earth Exists. They are not NASA. They are not affiliated with any major observatories. They are part of a growing network of citizen astronomers who had been tracking DRAMASIC on their own, independently using publicly available telescope data and sky survey archives. Some might dismiss amateur observations, but these are not kids with backyard telescopes. These are individuals with access to serious equipment, people who understand astrometry, orbital mechanics, and photometry. They cross-reference their findings with multiple data sources, comparing images from different observatories, running their own calculations, according to their analysis, published on October 22nd. The positional deviation was not static. It was increasing. 19 hours after the initial observation on October 21st, they ran another positional analysis. The divergence had grown. They calculated the rate at about 0.23 arc-minutes per hour. At that distance, this translates to a velocity change, nearly 4 kilometers per second, laterally. That is not drift. That is not measurement noise. It is a sustained deviation from the expected gravitational path. Let's put 4 kilometers per second into context. That is about 14,400 kilometers per hour. For reference, the fastest human-made spacecraft, the Parker Solar Probe, reaches speeds of about 192 kilometers per second at perihelion. But that is from falling toward the sun with a massive gravitational assist. We are talking about lateral movement here, perpendicular to the main trajectory. Such a velocity change requires a force. For a comet, that force would come from outgassing jets of sublimating ice, turning to vapor and pushing against the nucleus. But here is the problem. When comets outgas strongly enough to create measurable orbital changes, they become bright, very bright. You see giant plumes, expanding tails, a significant increase in magnitude. 3IATLAS was doing the opposite. JPL had predicted an apparent magnitude of around 14.8, which was already dim. It required quite good amateur telescopes to observe, but the actual readings showed the object at a magnitude of 15.1. About 26% dimmer than expected. This is counterintuitive. If the outgassing were strong enough to push the object 1 million kilometers off its path, we should have seen the brightest interstellar comet in history. Instead, it was dimmer than predicted, even though the James Webb Space Telescope confirmed it was losing about 25 kilograms of water per second. So, we have an object that is deviating from its predicted path in a way that suggests a forward thrust, while simultaneously appearing dimmer than it should. Despite confirmed active outgassing, these facts are not easily reconciled with standard cometary behavior. They create a tension that astronomers are trying to resolve, with increasingly creative explanations. Some have suggested that the nucleus is rotating in a way that hides the main active regions from Earth's view, possible but convenient. Others point to compositional anomalies detected by the Keck Observatory in August, unusual nickel emissions without corresponding iron, and a significantly low water content for an active comet. Perhaps this object's chemistry is so different from a solar system comet that it behaves in ways for which we simply have no model. It's also possible interstellar comets are very rare. We have only studied 3. Perhaps our assumptions about how they should behave are simply wrong. But then there is the third explanation. The explanation that most mainstream astronomers won't touch publicly but discuss privately. What if the deviation isn't random? What if there is something about 3IATLAS that is capable of adjusting its own trajectory? Not through natural outgassing, that is coincidentally pointed in a convenient direction, but through something more intentional. Avi Loeb has been saying this for months, rating the object a 4 out of 10 on his scale of potential technological origin. The accumulation of anomalies, he argues, pushes the probability of natural explanations below a comfortable threshold. Each individual oddity can be explained, but all of them together start to look like a pattern. The tracking community is not unanimous on this. Some groups have tried to replicate the Earth-based findings and have claimed they cannot confirm the same magnitude of deviation. Others say that their data shows similar trends, but attribute it to outdated orbital elements in the JPL database. Orbital elements are the mathematical parameters that define an object's path through space. They are refined as more observations become available. Perhaps JPL's last update was on October 10th, and by October 21st, those elements were old enough to cause a prediction error. Except, here's the thing. JPL updates orbital elements for near-Earth objects and significant comets frequently, especially for something as high-profile as 3IATLAS. The idea that they would let the data go stale for 11 days during its approach to perihelion seems unlikely. This is precisely the phase when tracking would be most critical, when observatories around the world are pointing their instruments at this object. When NASA coordinated observations from Mars orbiters, the Hubble and James Webb Space Telescopes, and ground-based facilities at 6 locations. David Szejda, another independent researcher, added fuel to this fire on October 20th as he was reviewing images from the LASCO CBA coronagraph. NASA's LASCO CBA, a solar telescope designed to observe the sun's corona. By blocking the bright disk, LASCO images the space around the sun, and comets occasionally pass through its field of view. Szejda documented something unusual across several frames. BAI-ATLAS appeared to show geometric light structures, not the circular, diffuse glow you would expect from a comet's coma, but rather sharp-edged patterns in one image. That light formed what he described as a plasma geometry resembling the number 10, before the object disappeared from the next few frames, then reappeared, and then vanished again. Now, LASCO images are notoriously difficult to interpret. You are looking at extremely faint objects through a coronagraph, designed to observe the sun, not for deep space imaging. Artifacts are common, and image processing can create false patterns. Cosmic rays hitting the detector create bright spots, and telemetry errors from the spacecraft create gaps in the data. Skeptics immediately pointed to these factors, what Szejda called geometry. They called noise. But here's what makes the claim harder to dismiss. Earth Exists conducted their own analysis of DRAMASIC using single-frame image enhancement techniques. No stacking, no processing beyond basic contrast adjustments. They saw similar patterns: green outer edges, a blue core, and pinkish regions arranged in distinct geometric sections. They compared this to reference stars in the same field of view. Sabre and Comet 2025 R2 Tianyuan. Those sources appeared symmetrical, perfectly circular standard stars. DRAMASIC did not. The coloration is consistent with the spectral analysis performed by the observatory back in August. Cyanogen, ionized nickel, hydrogen plasma. Each element emits light at specific wavelengths, creating distinct colors when you separate the spectrum. But normally, those emissions blend into a diffuse glow. The claim here is that they are spatially separated into defined regions, as if the plasma around the object is somehow structured rather than random. That would be consistent with controlled magnetic fields, organizing charged particles, the kind of behavior you'd see around a fusion reactor or a magnetized spacecraft, not a dirty snowball. I want to be careful here. Extraordinary claims require extraordinary evidence, and what we have right now are provocative observations from non-institutional sources. That doesn't make them wrong. Citizen science has a strong track record. Amateur astronomers discover comets, track asteroids, and even detect exoplanet transits. But it does mean the findings need independent verification from facilities with instruments that are calibrated and use peer-reviewed methodologies. So far, major observatories have not released data either confirming or denying these specific geometric pattern claims. What we have is silence, or, more accurately, the delayed release of high-resolution images from the Mars Reconnaissance Orbiter. It was supposed to image by ATLAS during its closest approach to Mars on October 3rd. Those images, with a resolution of about 30 kilometers per pixel, could potentially show details of its surface structure, perhaps even confirming whether the brightness distribution matched natural outgassing or something more organized. As of October 23rd, those images had still not been publicly released. NASA cited the government shutdown as the reason for the delay, but that explanation did not sit well with many observers. This was considered the most significant interstellar object to pass through the inner solar system in recorded history, and the data was being withheld during the most critical observation window. Perhaps there was nothing unusual in the images. Perhaps the high-resolution camera saw exactly what you would expect: a fuzzy blob with a tail, and NASA just hadn't gotten around to processing and releasing the files. Or perhaps what they saw required careful analysis, consultation, and verification before going public. We do not know. And that uncertainty created space for speculation to thrive. What we do know, what is documented and verifiable, is that multiple independent teams, using different methods claimed by ATLAS, was not following its predicted gravitational path. The deviations they were measuring, if accurate, would require forces beyond simple solar radiation pressure or symmetrical outgassing. Those forces would need to be sustained, directional, and significantly stronger than what we typically observe from comets, of a similar size and activity level. And all of this was happening in the final week before perihelion, as the object passed behind the Sun and became completely unobservable from Earth. October 29th, 2025. 1.356 astronomical units from the Sun, hidden in the glare. If you were designing an orbit to make a course change without being tracked, you could not pick a better moment. The Oberth effect, named after Hermann Oberth, states that the most energy-efficient time For a spacecraft to fire its engine is at the point of highest velocity, which is usually at perihelion. A small push applied when you are moving fast creates a much larger change in orbital energy than the same push applied when you are moving slowly. So, here we were, an object with a growing positional deviation, geometric light patterns that may or may not be real, a dimming trend that contradicted its confirmed activity, and within 7 days of that October 21st observation, it disappeared behind the sun at the exact moment any intelligent system would choose to make its move. The math worked a little too perfectly. The timing felt a little too convenient. And the lack of clear explanations from official sources created a vacuum that speculation rushed in to fill. By November 3rd, 3IATLAS would re-emerge. We would see if the deviation persisted, grew, or vanished. We would know if October 29th was just another perihelion passage, or if something had used those 8 days of concealment to adjust its course. Until then, we were left with data that did not quite fit, observations that did not quite align, and a growing sense that the universe might be about to remind us that we truly understand so little. The SETI protocol update of October 16, 2025, was a declaration on the principles concerning activities, following the detection of extraterrestrial intelligence, which had not changed much since 1989. That was the official document endorsed by 6 space and international astronomical organizations, which clearly stated what scientists should do if they detected a signal from an extraterrestrial civilization. Verify it independently. Notify the Secretary General of the United Nations. Share the data openly, and send no reply without international consultation. These principles have guided SETI research for over 3 decades, with only minor updates in 2010, to streamline the language and clarify procedures. On October 16, 2025, the SETI Committee of the International Academy of Astronautics, or IAA, announced a comprehensive revision, not minor tweaks, but a complete overhaul, expanding the scope, updating the protocols for modern technology, and adding new requirements that did not exist in previous versions. The timing of the release, during the exact period when 3IATLAS was generating maximum public interest and scientific debate, did not escape notice. The revised protocols had been in development for years. A working group was formed in 2022 to examine how SETI should adapt to a changing information environment, expand its search methods, and enhance international participation. They presented a draft at the International Astronomical Congress in Milan in 2024, gathered feedback, refined the document, and put it to a final vote at the IAA in Sydney in late September 2025. The October 16th announcement represented the official release following that vote, with full adoption expected before the end of the year. But perception is as important as reality, and in the public discourse, for casual observers, and SETI, updating its first contact protocols just as an anomalous interstellar object was approaching. Its perihelion looked like preparation for an imminent event. Conspiracy communities immediately connected the dots. SETI knows something. They are preparing. The protocols need updating now, not next year. Because something might happen in the coming months that requires those new theoretical frameworks. The more mundane explanation was administrative timing. The work of international committees moves slowly. The September IAA meeting in Sydney was the scheduled venue to vote on the revised document, regardless of what 3IATLAS was doing. The October announcement followed standard academic practice of releasing papers shortly after conference presentations. The correlation with the perihelion of 3IATLAS was a coincidence, not coordination, except the document itself undermined that benign interpretation. The preamble explicitly mentioned artificial intelligence, social media, and political chaos as factors shaping how detection announcements would unfold. It acknowledged that misinformation spreads faster than verification, that state and non-state actors might manipulate discovery claims for political advantage, and that protecting researchers from harassment had become necessary. These were not abstract concerns. They were a response to the current information environment, where the discussions about 3IATLAS had demonstrated every problem the protocols aimed to address. The new framework also expanded beyond radio signals. Previous versions focused almost entirely on electronic transmissions, the SETI model. The classic is to listen for intentional broadcast from distant civilizations. The 2025 revision includes technosignatures under any form whatsoever, such as waste heat from large structures, or biosignatures, and chemical and exoplanet atmospheres, and physical artifacts. That last category is new and important. Physical artifacts means objects like the DRAMASIC. The protocols now explicitly include scenarios where the detection is not a signal, but an object, a manufactured object, encountered directly. Principle number 7 is the most discussed change. It states clearly that, pending international consultation, no reply shall be sent to a confirmed detection. Previous versions suggested consultation but were vague on its enforcement. The new language is definitive. Do not reply. Consult first. The consultation must go through the United Nations Committee on the Peaceful Uses of Outer Space, or other broadly representative international bodies, single governments, organizations, or individuals, and cannot unilaterally speak for humanity. This represents a major shift in the power structure. Under the old protocols, whoever detected the signal had considerable discretion in how to respond. They were expected to consult, but were not legally bound to. The revised protocols create a stronger normative pressure, and against unilateral action. If you detect something and reply without United Nations involvement, you are violating internationally recognized scientific standards. That is not legal enforcement, but it is reputational and professional enforcement, which can be just as powerful in academic and government contexts. Principle 8 addresses ethics and law, requiring consideration of the potential impacts on human society, protecting discoverers from harassment, and adherence to legal frameworks governing space activities. This principle did not exist in previous versions. Its inclusion acknowledges that a detection would not be purely scientific. It would be political, social, and potentially dangerous for those involved. The scientists who detect extraterrestrial intelligence and could face death threats, veneration, government pressure, media harassment, or worse. The protocols now formally recognize that risk and call for protective measures. The document, and also establishes a post-detection subcommittee within the IAA's SETI committee. This standing group will provide support and advice if a detection occurs, and offering expertise on interpretation, communication strategies, and managing the broader implications. Having that structure in place before a detection means the response is not improvised. There is institutional memory, prepared procedures, and designated experts. That is the difference between chaos and coordination. A subtle but important change relates to data storage. The new protocols require that evidence be stored in multiple geographical locations using tamper-proof records. Blockchain is mentioned by name. The concern is data manipulation, either by discoverers who might fabricate evidence, or by external actors who might try to suppress or alter genuine findings. The distribution of and encrypted and time-stamped copies of the raw data across multiple secure repositories makes manipulation virtually impossible. Anyone can verify the original data against the stored copies, This level of data security was unnecessary in 1989. Back then, the threat model was simpler. You worried about false positives, instrument errors, and misidentifications, natural phenomena appearing as artificial signals. You didn't worry about deepfakes or AI-generated false data, coordinated disinformation campaigns, or governments suppressing discoveries. The Internet changed everything. The new protocols reflect that reality. Another addition is frequency protection. If the detection occurs via electronic transmission, the revised protocols call for petitioning the International Telecommunication Union to protect the relevant frequency band from interference. This provides a legal mechanism to prevent terrestrial broadcasts, and that might jam or overwhelm the signal. It's a practical measure that also signals seriousness. You don't allocate international radio spectrum protection unless you are treating the detection as real and important. The community consultation process that shaped these revisions, and is noteworthy. The working group didn't just work internally. They used surveys, at workshops, and engaged early career SETI researchers, those who will inherit these protocols. They even used ChatGPT to analyze feedback, a detail explicitly mentioned in the paper, which is a remarkable transparency about methodology. But it's also an acknowledgement that AI is now an indispensable part of the scientific process. If you're writing protocols for detecting extraterrestrial intelligence, you can't ignore that human intelligence has been augmented by artificial systems. Critics have pointed out that the protocols, however well written, have no enforcement mechanism. SETI is a scientific community, not a government. The Declaration of Principles is voluntary. Signatories agree to follow them, but there is no penalty for violation beyond reputational damage. If a rogue researcher or nation detects a signal and replies without consultation, the protocols cannot stop them. They can only create social and professional pressure against that action. But that pressure is significant. Science runs on reputation. Violating widely accepted ethical standards can end careers, damage institutions, and isolate violators from collaborative networks. Most scientists care deeply. Their professional standing. The revised protocols leverage that to create incentive structures, so that favor responsible behavior, even without legal force. The question of timing still remains. Why finalize and publish now? The working group's efforts began in 2022, before 3IATLAS existed. The Milan draft in 2024 predated most of the widely known object anomalies. The Sydney vote in September, and happened weeks before perihelion. At each stage, the process was following its own timeline, and independent of any interstellar visitors. However, the final publication in mid-October, when global attention was focused on an object and of potential artificial origin passing through our solar system, created an unavoidable perception of a link. Perhaps that perception is useful. If 3IATLAS turns out to be natural, the protocol update, and still serves future preparedness, but if the observations in November and December reveal something else, necessitates invoking these protocols. Having them newly updated and publicly available ensures that everyone knows the procedures. There is no ambiguity about what should happen next. The international community had agreed on the theoretical framework just weeks before it might be needed. Skeptics argue that this is projection, reading intent into a coincidence. The protocols were being updated regardless of the timing of their publication, following academic convention. The fact that 3IATLAS became interesting during the same time frame does not imply causation. The scientists working on the revision did not coordinate with the astronomers tracking the object. These are separate communities, with separate workflows that coincidentally overlapped in time. However, the institutions do talk to each other. The SETI committee of the IAA includes members who were aware of DRAMASIC, such as Michael Gazet, the lead author of the revised protocols, who works at institutions involved in the astronomical observations. Another author, Catherine Denning, specializes in the anthropological aspects of contact scenarios. These are not people operating in an information vacuum. They knew about the object, they knew about the anomalies, and they knew that perihelion was approaching as they finalized the document. Whether or not that knowledge consciously influenced the timing, the result is the same. Humanity entered the post-perihelion observation phase of DRAMASIC with comprehensive, updated protocols to respond to a detection of extraterrestrial intelligence. If those protocols were needed, they were ready. If they were not needed, they still represented the most thoughtful framework ever developed for one of the most consequential scenarios that we can imagine. The document included something previous versions lacked a clear statement on when these protocols should be used. They apply when evidence indicates a deliberate transmission or construction by non-human intelligence, not just any anomaly, not a hard-to-explain natural phenomenon. Evidence of intent, design, and purpose. That is the threshold. Below it, you are doing interesting science. Above it, you are in the territory of a contact scenario, where these protocols activate. DRAMASIC was on that threshold. The 8 anomalies suggested something unusual, but did not definitively prove intent. If post-perihelion observations revealed orbital changes inconsistent with natural forces, if we detected radio transmissions, if secondary objects detached and navigated independently, then intent would become hard to deny. At that point, these protocols are not theoretical. They are operational guidelines for managing the most important discovery in human history. The revised protocols would not prevent chaos if that scenario unfolded, but they do provide structure. They assign responsibilities, they establish communication channels, and they protect the researchers and the integrity of the data. They ensure international participation rather than unilateral action. In a situation where everything would be unprecedented and many things would go wrong, having any framework at all is better than complete improvisation. SETI researchers have waited for decades for a detection, with most assuming it would be a radio signal from a star many light years away, allowing time for a careful response without immediate consequences. DRAMASIC, if it were a detection, was very different. It was here, it was close, and it was moving through our planetary system, right now. The response timeline was a matter of weeks, not years. The luxury of slow deliberation did not exist. That urgency might explain why the protocols emphasize immediate steps, independent verification, data security, informing the Secretary General. These are not long-term strategic recommendations. They are acute phase crisis management. Do these things first, within hours or days, to establish the facts and prevent misinformation from dominating the narrative. Longer-term responses can follow once immediate stability is achieved. On October 16, 2025, Mr. City updated his scenario for contact, 13 days before DRAMASIC reached perihelion, 18 days before it was set to re-emerge from behind the sun for post-perihelion observation. The protocols were published, voted on, and ready for implementation. Whether they would be needed or not was a question that November and December would answer, but their availability, newly revised and internationally endorsed, came just when they might matter most, either extraordinary foresight or an extraordinary coincidence. Time would tell which. This disappearance behind the sun has a specific term in orbital mechanics that most people never encounter, unless they study space travel or planetary science. Solar conjunction. It sounds technical, almost administrative. But what it describes is remarkably simple. It's when an object in space passes directly behind the sun, from Earth's perspective, becoming completely invisible to our telescopes, because the sun's overwhelming brightness obscures anything near it. With 3IATLAS, the solar conjunction occurred on October 21st, 2025, the exact same day. Those orbital deviations began to appear in the independent tracking data. Think about the geometry for a moment, Earth, the Sun, and Atlas, all in a straight line with the Sun in the middle. From our perspective, the object disappears into the glare of the Sun. Not behind the physical disk of the Sun. That would require an arcsecond precise alignment, but close enough that the Sun's corona, its superheated outer atmosphere, which extends for millions of kilometers into space, creates a blinding backdrop, making observation impossible. Even for our most powerful coronagraphs, instruments designed specifically to block the solar disk and study the region around it, struggle to pick out faint comets when they are this close to solar alignment. This alignment doesn't last forever. Objects move, Earth orbits, the geometry shifts, but for 3IATLAS, the timing created something unusual. The solar conjunction on October 21st meant the object entered its unobservable zone 8 days before perihelion. 8 days before its closest approach to the Sun on October 29th. At 11:36 Coordinated Universal Time, those 8 days represented the period when the object would accelerate to its maximum velocity, experience peak solar radiation, and, if it was anything other than a natural comet, perform the most critical phase of its mission profile. Let's talk about what happens at perihelion from an engineering perspective. If you are sending a probe to another star system, and you want it to perform maneuvers in that system, you don't do it randomly. You follow the principles of orbital mechanics that have governed space travel since we first started leaving Earth's atmosphere. The Oberth effect, formulated in the 1920s, tells us that the most efficient time to change a spacecraft's trajectory is when it's moving at its highest velocity. The calculation is very simple. Kinetic energy equals 1/2 mass times velocity squared. That squared term is very important. If you are moving at 10 kilometers per second and you add 1 kilometer per second of thrust, the change in energy is much smaller than if you were moving at 50 kilometers per second and added that same 1 kilometer per second. The faster you go, the bigger the energy punch you get from each unit of thrust. For 3IATLAS, maximum velocity occurs at perihelion, at that point falling toward the Sun's gravity well. The object would be moving at about 68 kilometers per second relative to the Sun. If you wanted to release probes that could intercept planets in the inner solar system, perihelion is the time you would do it. A small velocity change at that moment, perhaps 10 or 15 kilometers per second in the right direction, could redirect a small probe toward Earth, Mars, or Venus at a relatively modest fuel cost. Waiting until you are farther away and moving slower, and the same maneuver costs exponentially more energy. This isn't speculation about alien engineering. This is how human spacecraft operate. When we send probes to the outer solar system, we use gravity assists to accelerate, and we time our engine burns for moments of peak velocity. The Voyager and New Horizons missions, every deep space probe, follows these principles because physics doesn't care about your intentions. The math works the same whether you're NASA or something that evolved under another star. Now, let's overlay that engineering reality onto the timeline of 3IATLAS. October 21st. Solar conjunction begins. October 29th. Perihelion passage at 1.356 astronomical units. During those 8 days, Telescopes on Earth see nothing. Mars orbiters might catch a glimpse, if they look at the right time. But the Sun's position relative to Mars means that even those observations are limited. The European Space Agency's JUICE spacecraft, currently between Earth and Jupiter on its way to the outer system, will attempt observations in early November. But during that critical perihelion window, DRAMASIC operates in the dark, completely from our perspective. The distance of 1.356 astronomical units places it about 203 million kilometers from the Sun. For reference, Earth orbits at 1 astronomical unit, Mars at about 1.5. Perihelion for DRAMASIC places it closer to the Sun than the orbit of Mars, but farther than Earth's. That's a position that provides tremendous solar power to generate energy if you are a technological system, but not so close that the heat would vaporize metal or destroy electronics. With proper shielding, a habitat designed to operate in interstellar space, shielded against cosmic radiation and temperatures near absolute zero, would find this distance almost ridiculously warm. The solar radiation flux at that distance would deliver about 33 gigawatts of power to the object's surface, assuming Avalon's minimum diameter estimate of 5 kilometers. 33 gigawatts is about the output of 30 large nuclear power plants. If even a small fraction of that could be captured and converted to useful energy, you'd have more than enough to run any propulsion system, communications array, or manufacturing process imaginable. Again, this doesn't imply DRAMASIC is technology. It just points out that if it were, perihelion would be the ideal moment to do whatever it came here to do, and a solar conjunction ensures we won't be tracking it when that happens. The orbital parameters tell a different story, one that's easy to miss if you're not looking for it. DRAMASIC has an eccentricity of 6.137. Eccentricity is a number that describes how elliptical or hyperbolic an orbit is. A circle has an eccentricity of 0. Earth's slightly elliptical orbit has an eccentricity of 0.017. Anything over 1.0 is a hyperbolic orbit, meaning the object is not bound to the Sun and will eventually escape. 6.137 is extremely hyperbolic. The orbit is almost a straight line, barely curved by the Sun's gravity. This object is passing through our solar system at such a high speed that even the gravitational pull of our star only slightly bends its path. That extreme eccentricity also means something else. The time spent in the inner solar system is minimal. DRAMASIC isn't spending months slowly falling toward the Sun. Like a comet from the Oort cloud, it arrived from interstellar space at 58 kilometers per second and will leave at about the same speed. The entire pass, from its discovery in early July to its departure from the inner system in late December, lasts about 6 months. Compare that to long-period comets, which can spend many years in the inner system, or short-period comets that return every few years or decades. This is a flyby in the truest sense, a brief interaction with the Sun before continuing on into the galactic disk. But this is where it gets interesting. The orbit isn't just hyperbolic, it's aligned. The orbital plane of DRAMASIC matches the ecliptic plane, the plane defined by Earth's orbit around the Sun, to within 5 degrees. Most objects arriving from interstellar space should approach from random angles. The galaxy has no regard for our ecliptic plane. Comets from the Oort cloud, gravitationally bound to the Sun, but only just barely, come from every imaginable direction. That's why we see them scattered across the sky. Retrograde orbits, prograde orbits, high inclinations, low inclinations, there's no preferred direction. DRAMASIC is different. Its 175-degree inclination means it's moving retrograde, opposite to the direction the planets orbit. but the plane itself is nearly aligned with ours. Loeb calculated the probability of that alignment happening by chance at about 0.2%. That's not impossible, 2 in 1,000, but it's unusual enough to raise an eyebrow. An orbit aligned with the planetary plane makes interception easier. If you were trying to release probes that would encounter multiple planets, starting from an orbit already in the plane of their orbits saves a tremendous amount of fuel compared to making large plane changes, which is one of the most expensive maneuvers in orbital mechanics. Add to that the timing of DRAMASic's arrival, which brought it within tens of millions of kilometers of Mars on October 3rd, Venus on November 3rd, and Jupiter on March 16th, 2026. The probability of an interstellar object randomly happening to pass close to 3 major planets during its flyby is vanishingly small. Loeb and his colleagues calculated it at about 0.005%, or 5 in 100,000. These are not impossible odds, but they are beginning to accumulate in ways that trigger the pattern recognition circuits in our brains. Of ours brightens. Is it a coincidence that perihelion occurs during solar conjunction? From a physics perspective, there is no connection. Solar conjunction is about Earth's position relative to the object's orbit. Perihelion is about the object's closest approach to the Sun. They are independent parameters. The fact that they occur 8 days apart creates a window where the object is both at peak velocity and hidden from observation. It's just how the orbital geometry plays out. But if you were planning an interstellar mission and could choose your approach vector, you would certainly design it this way, hiding the most critical phase behind the brightest object in the system. The question becomes testable on November 3rd, when DRAMASIC reemerges from behind the Sun. We will have a clear line of sight again. Many observatories will track its position, measure its brightness, and analyze its spectrum. If the orbital deviations observed in late October are real and sustained, they will appear in the post-perihelion data. The deviation will be greater, the divergence from purely gravitational motion more apparent. If those deviations were measurement errors or temporary outgassing anomalies, the object will return to its predicted path, and all speculation will evaporate. But there is a third possibility that keeps astronomers awake at night. What if the orbit matches the predictions perfectly after perihelion, but the spectral signature changes? What if the composition is different? The activity level drops or spikes in unexpected ways. The polarization shifts. Loeb has publicly stated that if DRAMASIC survives perihelion intact and continues to show natural cometary features, he would downgrade it to a Category 2 on his scale, still anomalous, still interesting, but probably natural. However, if the post-perihelion observations reveal anything unusual, changes that suggest the object is no longer the same system we were tracking before it disappeared, then a Category 4 might not be high enough. There is historical precedent for comets behaving strangely at perihelion. They disintegrate due to thermal stress. They have unexpected outbursts as new ice is exposed. They fade quickly if their reservoirs of volatiles are depleted. Comet Ison, in 2013, completely disintegrated during its perihelion pass, providing a spectacular example of how this environment can be violent. But Ison was on a much closer orbit, grazing just over 1 million kilometers above the Sun's surface. DRAMASIC is at a comfortable distance of 203 million kilometers, far enough that thermal stress should be manageable even for a rubble pile that is loosely bound. Mass estimates suggest something substantial, at least 33 billion tons, based on the lack of non-gravitational acceleration. Despite its visible outgassing, that mass, combined with a diameter of about 5 kilometers, implies an object that is either extremely dense or has significant structural integrity. Most comets are loosely bound ice and rock, porous structures that sublimate and shed material easily. If DRAMASIC is this large and has not yet shown an orbital change from outgassing, then that outgassing is perfectly symmetrical, which seems unlikely given the observed anti-tail that existed in July and August, or the object's mass is large enough that even vigorous outgassing produces a negligible recoil. Either way, it is built to last. Perihelion at 1.356 astronomical units will not destroy it. The question is, what does it do during those hidden days? Will it disintegrate naturally, creating fragments that will become visible as they separate in the following weeks? Does it release material intentionally, with smaller objects beginning their own orbits toward specific targets, or will it simply continue on its hyperbolic path, unchanged, except for the expected brightening and a possible increase in outgassing from solar heating? We are about to find out by the time November arrives. Comet Atlas will complete its close approach, absorbing 33 GeA of solar radiation in a few days, and if it is anything other than a comet, it will perform any maneuvers or deployments planned for this moment. Post-perihelion observations will either confirm it is natural, revealing nothing unusual despite previous anomalies, or they will show something that forces us to seriously consider the technological hypothesis. There is no longer a middle ground. The data will either support natural explanations, or it will not. Somewhere between Earth and that hiding point behind the Sun for 8 days, when no telescope can track it, Comet Atlas will do what it came here to do. The brightness paradox. Brightness in astronomy is not just about the amount of light reaching your telescope. It is a diagnostic tool, a way to read what an object is made of, how it behaves, and how much surface area is exposed to solar radiation. When a comet approaches the Sun, predictable things happen. Ice sublimates, turning directly from a solid to a gas, which then drags dust particles off the nucleus, creating the familiar coma and tail. The coma scatters sunlight, making the comet appear brighter. The closer to the Sun, the more heat, the more sublimation, and the brighter the show. This relationship is reliable, so much so that astronomers can predict a comet's brightness months in advance with reasonable accuracy. Comet Atlas broke that pattern. The predictions from the Jet Propulsion Laboratory, based on standard models of cometary behavior and the object's known size and orbit, expected an apparent magnitude of around 14.8 by late October. Magnitude is a logarithmic scale, where smaller numbers mean brighter objects. The difference between magnitude 14 and 15 might not seem like much, but each full magnitude represents about 2.5 times more or less light. So, a magnitude of 15.1, which is what observers actually measured, means the object was about 26% fainter than expected. That might seem like a small discrepancy. Comets are notoriously unpredictable. Their activity waxes and wanes. Rotation can hide or expose active regions. Dust production varies based on composition. All of this creates uncertainty in brightness predictions. But here is what makes this particular dimming so puzzling. The James Webb Space Telescope, or Webb, confirmed active outgassing. Spectroscopic observations showed carbon dioxide, water vapor, carbon monoxide, cyanide, and ionized nickel were streaming from the nucleus. The production rates measured by Webb showed the object was losing about 25 kilograms per second. In late August observations, that is not a dormant comet, it is an active system, shedding material at a rate comparable to many solar system comets. When you have that much outgassing, you create a substantial coma, a cloud of gas and dust surrounding the nucleus. That coma scatters sunlight. The more material in the coma, the more scattering. The brighter a comet appears from Earth, the more active it is, and standard photometric models account for this. You measure the rate of gas production, estimate the dust-to-gas ratio based on the spectrum, calculate how much sunlight that dust will scatter, and predict the resulting brightness. For Comet Atlas, those calculations suggested a magnitude of 14.8. Instead, telescopes saw 15.1. The first explanation that comes to mind is its composition. Perhaps Comet Atlas has an unusually low dust-to-gas ratio. Pure gas does not scatter light as efficiently as dust particles. If the object is releasing mostly volatile substances with very little particulate matter, the coma would be less reflective than expected, creating a dimmer appearance despite high activity. That's plausible. Interstellar comets could form under different conditions than solar system comets. Different temperatures, different pressures, and different chemical environments could create objects with an unusual ratio of ice to dust. But spectroscopic analysis showed signs of silicate dust and organic compounds. That type of particulate matter should scatter light efficiently. The spectrum was not that of a pure gas coma, as solid matter was present. So the low dust hypothesis doesn't quite work, unless the dust particles are much smaller than typical cometary dust. Very small particles, smaller than the wavelength of visible light, scatter less efficiently. They could explain the reduced brightness despite the confirmed presence of dust. That is possible, although it requires another unusual characteristic to be layered onto an already unusual object. The second explanation involves geometry and viewing angle. Comets are not spherically symmetrical. They have jets, which are localized active regions where sublimation is concentrated. If the main active areas on Comet Atlas were pointed away from Earth, we might be seeing mostly sunlight reflecting off the nucleus itself, rather than the bright, scattered light from the coma's dust. This happens occasionally with solar system comets. A comet can be very active, but appear relatively faint from Earth if we are viewing it from an unfavorable angle. Except we have visual confirmation from images of a visible coma. Hubble images from July show a distinct teardrop-shaped cocoon of material trailing the nucleus. The antitail observed throughout August demonstrated asymmetrical outgassing strong enough to create a visible structure pointing toward the sun. If the active jets were strong enough to create those features, they should have been bright enough to appear in the integrated brightness measurements. The viewing angle explanation only works if the geometry changed significantly between the Hubble observations in July and the brightness measurements in October, and there's no clear reason why that would happen. Then there's the possibility of surface changes. Comets can develop an insulating crust, layers of dust and organic material that slow the rate of sublimation. As the surface heats up, fresh ice sublimates rapidly upon its first exposure to solar radiation. Over time, the most volatile ices are lost, leaving behind a lag deposit of less volatile material that acts like a blanket, slowing the transfer of heat to the subsurface ice. This process causes comets to dim as they age. An interstellar comet has likely spent billions of years in deep space, at temperatures near absolute zero. It's possible that all its volatile surface ice was locked beneath a crust. So, as it approaches the sun, that crust heats up, but not necessarily, leading to a corresponding increase in activity. The object could be outgassing vigorously from localized fissures or weak points, while most of its surface remains dormant. That scenario is consistent with some observations of high activity in specific regions, creating the observed mass loss but an overall dim appearance because most of the surface isn't contributing to the coma. It's a plausible, natural explanation. But it raises another question if the surface is largely inactive. Where is all that carbon dioxide coming from? Webb has measured the production of significant carbon dioxide, much higher than the rate of water production. The sublimation of carbon dioxide requires specific temperature thresholds. It suggests either exposed carbon dioxide ice or subsurface reservoirs connected to the surface through fissures or vents. Either way, you would expect to see regional brightening around those active areas. Hotspots would appear in high-resolution images. High-resolution camera observations from the Mars Reconnaissance Orbiter could potentially resolve this. With a pixel scale of about 30 kilometers, they would be able to distinguish between a uniformly outgassing object and one with bright active regions concentrated in specific areas. But those images have not yet been released. Without them, we are left to infer the structure from photometric measurements and low-resolution spectroscopy, trying to build a three-dimensional model from a two-dimensional shadow. There is another angle to consider here, one that sounds almost conspiratorial, but which emerges from the data itself. What if the object were intentionally minimizing its brightness? That sounds absurd for a natural object. Comets don't have intentions. They react to solar heating, according to the laws of thermodynamics. But if Bialis were artificial, a probe or a spacecraft rather than a comet, brightness management would be a fundamental operational parameter. Think about human spacecraft design. We coat surfaces with specific materials to control thermal properties and to minimize reflectivity where needed. Stealth satellites use low albedo coatings to reduce their visibility. If you were sending a probe through interstellar space and you wanted it to pass through a planetary system unnoticed, or at least unremarkable, you would design it to look like natural debris. But looking natural spectroscopically, having the right chemical signatures, is easier than perfectly matching the brightness curves. You could intentionally outgas water and carbon dioxide, mimicking cometary activity. Controlling the precise magnitude at which you appear requires either a perfect match of surface properties or deliberate dimming through geometry, orienting reflective surfaces away from observers. I know how this sounds. We are reaching for technological explanations for what could simply be an unusual but natural comet with an atypical composition and structure. The brightness paradox itself doesn't prove anything. Comets surprise us frequently. They have unexpected outbursts. They dim without warning. They break into fragments. They exhibit jets that defy models. The fact that DRAMASIC is dimmer than predicted is not, in itself, extraordinary. But place it in context an object that is dimmer than expected despite confirmed high activity. An object that shows an orbital deviation from its predicted path. An object with geometric light patterns. Could point to the structured plasma fields of an object with compositional anomalies, such as nickel emission, without corresponding iron. An object arriving on an orbit optimally aligned with the planetary plane, and timed to pass multiple planets. While each individual piece might be explainable, together they form a pattern that is harder to dismiss. Brightness measurements continued throughout early November as DRAMASIC emerged from behind the Sun. Observatories around the world would monitor its magnitude, looking for the expected post-perihelion brightening. Standard comet models predict a significant increase in brightness after perihelion as new material is exposed, and outgassing increases from solar heating. If DRAMASIC follows that pattern, brightening to magnitude 12 or 11, as some predictions suggest, it would support natural explanations, making the October dimming just an artifact of observation geometry, or a temporary decrease in activity. But if the object remains dimmer than predicted, if it continues to perform below its expected brightness, despite its proximity to the Sun and confirmed outgassing, then we have a persistent anomaly that requires explanation. The systematic dimming would imply something about the object's structure or behavior that current comet models do not capture. Either our understanding of interstellar comet composition is fundamentally wrong, or B, Atlas is managing its observational signature in ways that natural objects do not. Polarization measurements add another layer. In late September, the Very Large Telescope team observed BI-ATLAS and found negative polarization values. The degree of polarization describes how light waves are oriented after scattering off particles. Different materials and particle sizes produce characteristic polarization signatures. Most comets show positive polarization, which means the scattered light waves, a line perpendicular to the scattering plane, BI-ATLAS, however, showed strong negative polarization, with waves aligning parallel to the scattering plane. That behavior is almost unprecedented in comets. The VLT team noted that the probability of such extreme polarization occurring naturally in a comet is less than 1%. Negative polarization can occur with very specific particle size distributions and compositions. Laboratory studies show that certain types of dust produced under controlled conditions can exhibit this, but finding it in an active comet, where particle sizes vary widely and the composition is mixed, is extremely rare. It suggests either the dust from BI-ATLAS is remarkably uniform in size, with all particles clustered around some optimal diameter to produce the negative polarization, or the composition consists of materials with unusual optical properties, not typically seen in solar system comets. Or a third option, the polarization is not from scattered sunlight at all. It is emission from some other process that happens to produce polarized light. Synchrotron radiation, from charged particles spiraling in magnetic fields, produces highly polarized emission. So do certain plasma processes. If what we are seeing is not reflected sunlight, but rather emission from a magnetized plasma surrounding the object, the polarization signature would look very different from typical cometary dust scattering. This is speculative, venturing into explanations that require exotic physics or technological processes. But when standard models fail to explain the observations, you have to consider alternatives. The brightness paradox will not be resolved through observation alone. We need close-up images of the resolved surface features and thermal mapping to show where heat is being generated and radiated. We need to distinguish between a largely inactive, cold surface with localized hotspots and a uniformly active surface that is somehow dimmer than expected. The difference is critical for determining what ATLAS truly is. For now, we watch and wait for November 3rd to bring renewed visibility. October 19th. It brings the closest approach to Earth at 1.8 astronomical units, about 269 million kilometers. That's not close enough for amateur telescope observation, but professional facilities will have excellent viewing geometry. The light curve throughout November, and December will tell us whether the October dimming was an anomaly or a persistent feature. If the object brightens as predicted, following standard cometary behavior, the anomaly will fade into statistical noise. If it remains dim, or worse, grows dimmer, while maintaining a high outgassing rate, then we have something that defies a comfortable explanation. The universe is full of objects we don't fully understand. Interstellar space is vast and ancient, creating conditions that we cannot easily replicate or study. The Atlas flyby. Being unusual doesn't make it artificial, but being unusual in predictable ways, following patterns that coincidentally align with what you would design if you wanted to traverse a planetary system efficiently while minimizing detection. That's when unusual starts to look like something else entirely. Geometric plasma structures. Plasma is the fourth state of matter, after solid, liquid, and gas. When you heat a gas enough, electrons are stripped from their atoms, creating a mixture of charged particles that behaves very differently from neutral matter. Lightning is plasma. The sun's corona is plasma. The aurora flowing across the sky is plasma. Interacting with Earth's magnetic field, it's everywhere in the universe, making up 99% of visible matter. But it's also notoriously difficult to control. Plasma reacts to electromagnetic fields, flowing along magnetic field lines, forming structures and instabilities that challenge our best physical models. Natural plasmas in a cometary environment are chaotic. The solar wind carries charged particles, streaming from the sun at hundreds of kilometers per second, interacting with the comet's coma. That interaction creates a bow shock, a boundary where the wind slows down and compresses. Behind the shock, you get complex turbulence, eddies, and irregularities. The result is an uneven, diffuse glow. When you image a comet at certain wavelengths, you can see asymmetries, brighter regions where outgassing is stronger. But overall, the light distribution smooths out, following the density gradient of gas and dust in the coma. What you don't typically see is sharp, defined geometry, or color separation into distinct regions, X-shaped patterns, or other regular shapes. Physics doesn't support that. A plasma without a strong external organizing force spreads out, diffuses, following pressure gradients and magnetic field lines, which are themselves tangled and irregular around a comet. Getting structured geometry requires either very specific conditions or active field management. On October 20th, David Cezida reviewed images from NASA's LASCO C3 coronagraph. These instruments photograph the space around the sun by blocking the sun's disk with an occulting disk to reveal the faint corona and any objects that pass through the field of view. Comets occasionally appear, usually as fuzzy blobs with tails streaming away from the sun. Cezida found ATLAS in multiple frames. What caught his attention was not the object's presence, but rather its appearance, where the distribution of light around ATLAS in one image formed what he described as a cross-shaped pattern, not a perfect geometric cross like you would draw on graph paper, but a distinct four-fold symmetry with brighter regions extending in perpendicular directions. Then, in the next few frames, the object disappears completely. LASCO takes images at regular intervals, typically every 12 or 30 minutes, depending on the observation program. Objects in the coronagraph's field of view should appear in consecutive frames as they move through space. They might change brightness slightly due to observation geometry or changes in activity, but they don't just disappear and reappear unless something dramatic happens. ATLAS disappeared for several frames, then reappeared, then vanished again. The pattern repeated multiple times throughout the observation sequence. Cezida documented this and shared the findings publicly, arguing that the disappearances and the geometric pattern suggested something unusual about the object's behavior or structure. Skeptics immediately offered alternative explanations. LASCO images are notoriously difficult to interpret. The instrument was not designed for deep space observations. It's optimized for studies of the solar corona. This means its sensitivity and calibration are tuned for specific ranges of brightness and wavelength. Faint objects near the detection limit can appear and disappear due to image processing artifacts, a cosmic ray hitting the detector, or simple signal-to-noise fluctuations. If ATLAS was at the very edge of LASCO's detection threshold, frame-to-frame variations in the background noise could make it visible in some images and invisible in others. The cross-shaped pattern could be a diffraction artifact. Coronagraphs use complex optical systems with multiple disks, occulting disks and baffles to block sunlight. Bright point sources sometimes create cross-shaped diffraction spikes due to the edges of these optical elements. Stars in LASCO images often show this pattern. If Atlas had a bright central region, a concentrated nucleus, or a specular reflection point, it could theoretically produce similar diffraction effects. But then there was the group that had documented the orbital anomalies, which performed an independent analysis. They weren't looking at LASCO images. They were processing their own observations from ground-based facilities, using standard astronomical CCD cameras attached to moderate aperture telescopes. They applied single-image enhancement, adjusting contrast and brightness to bring out faint details, but they did not stack multiple exposures or use heavy processing that could create artifacts. Their images showed color separation in the coma, green outer regions, blue central areas, and pinkish regions distributed around the nucleus. To verify this was not an artifact, they imaged reference stars in the same field of view, such as Spica, one of the brightest stars visible from Earth, appears as a tight, circular point spread function. With normal color balance, Comet C 2025 R2 Swan, another active comet, visible in the same area of the sky, shows a typical cometary appearance with a circular coma, a diffuse gas cloud, and a faint tail, with no geometric patterns, no unusual color separation. Apart from the common faint green in the cometary coma from diatomic carbon emission, by ATLAS in other color regions they measured, corresponds to known emission lines. A green color from ionized cyanogen, a blue color from hydrogen plasma, and a pink color likely from a mixture of ionized carbon and other species. These are not unexpected chemicals. The CAD Observatory confirmed the presence of cyanogen back in August. Hydrogen emission is standard for comets. What is unusual is the spatial distribution. Normally, these emission regions overlap. You do not get a clean separation because the gases mix as they expand from the nucleus. The chaos of solar-wind interactions and thermal diffusion blur any initial structure within seconds to minutes. After the material leaves the surface, maintaining distinct color regions requires something to prevent mixing. In laboratory plasmas, that is usually a magnetic field. Charged particles spiral along magnetic field lines, confined to specific regions depending on the field geometry. If you arrange the magnetic fields carefully, you can create structured plasmas with well-defined boundaries between regions of different temperatures or compositions. We do this in fusion reactors. We do it in plasma thrusters for spacecraft. It requires active field coils or permanent magnets, with specific configurations. The natural magnetic fields around comets are weak and irregular. Comets do not have internal dynamos like planets. They are not large enough or conductive enough to generate strong, self-sustaining magnetic fields. They carry, frozen in magnetic fields embedded in the material from their formation environment. But these fields are typically chaotic, without large-scale organization. The solar wind carries its own magnetic field, but that is also disorganized. At the small scales relevant to a cometary coma, could BiATLAS have an unusually strong internal magnetic field, or a well-organized one? It is not impossible if the object formed in a region with strong ambient fields, perhaps near a massive star or in a molecular cloud. With aligned magnetic fields, it could have retained some of that structure. Certain minerals, like magnetite, can preserve magnetic fields over geological timescales. If BiATLAS has a high concentration of magnetic minerals, and they are aligned, you could theoretically get a weak but organized field. But here's the problem with that explanation. The field would need to be strong enough to organize the plasma over distances of hundreds to thousands of kilometers. The scales involved are not the nucleus itself, which might be 5 to 10 kilometers wide, but the coma, the expanding gas cloud that can reach 10,000 kilometers in size for active comets, creating Structured plasma at those scales requires field strengths far beyond what comes from the chemistry remaining in the rock could provide the moving charged particles required to actively generate current loops, creating magnetic fields through electromagnetic induction. The alternative is that what we're seeing isn't a plasma structure, but an optical effect, the selective scattering of sunlight by particles with specific properties, distributed in patterns around the object. Some dust components preferentially scatter light at specific wavelengths. Specifically, if Atlas is ejecting different types of dust from different regions on its surface, and if those dust types separate spatially as they move away from the nucleus based on Cezanne composition, you could create regions of different colors. This happens to some extent in all comets, as heavier particles follow slightly different trajectories than lighter ones. But achieving a clean separation observable from Earth would require the ejection processes to be extremely organized. Each type of material would need to come from distinct surface regions and maintain that separation as the coma expands. That's very difficult, but not physically impossible. Some comets do show jets with distinct colors when imaged in narrow-band filters that isolate specific emission lines. What bothers careful observers is the combination of the color separation, plus the geometric pattern, plus the disappearing act in the LASCO images, plus the orbital anomalies, plus the brightness paradox. Each piece has potential natural explanations that stretch, but do not break. The laws of physics. All of them together start to feel less like a coincidence and more like a system with behaviors that we are ill-equipped to interpret. There is a concept in SETI research known as the Drake equation, but there is another, less famous theoretical framework called the Rio scale. It's designed to quantify the significance of SETI detections, ranking a signal from 0, meaning it's clearly natural or noise, of human origin, to 10, meaning it is unambiguous evidence of extraterrestrial technology. The scale considers factors like distance from Earth, the information content of the signal, and whether it can be independently verified, and how well it fits with natural versus artificial explanations. Atlas doesn't fit neatly on the Rio scale, because it's not a signal, it's a physical object. But if you were to apply the same logic, the geometric plasma structures would score somewhere in the range of being inconclusive, not easily explained by standard models, requiring more observations from independent sources to verify, yet potentially natural, if you allow for unusual but physically permissible conditions. But when you accumulate enough anomalies, it becomes harder to justify ignoring them than investigating them seriously. The plasma models also raise practical questions about observational priorities. If what we are seeing are real structures in the coma, not artifacts or illusions, then we need high-resolution spectroscopy, not just single-wavelength images, but hyperspectral data cubes that show how each emission line is spatially distributed. That kind of data would immediately distinguish between organized plasma with sharp boundaries and complex optical effects from dust scattering. It would tell us whether magnetic fields are involved, and whether electric currents are flowing through the coma. Could something about this object be creating an electromagnetic environment unlike any comet we have studied? Observations from a visiting spacecraft in early November could provide some of that data. The spacecraft has a spectrometer and a particle detector. It could characterize the plasma environment if it gets close enough and points its instruments correctly. But user is optimized to study the moons of Jupiter, not interstellar comets. The observation window will be limited, and the geometry may not be ideal to resolve fine spatial structure. Ground-based observations after Biolus emerges from solar conjunction will continue. Amateur astronomers with good equipment can take images showing the overall coma morphology. Professional facilities with adaptive optics and integral field spectrographs can perform detailed analysis. The question is whether the patterns are persistent or are they transient features. Specific to the object's state in October, if the geometry disappears, we can argue that it was always artifacts or temporary phenomena related to the perihelion passage. If the patterns remain, if subsequent observations by multiple independent groups all confirm a structured light distribution with color separation and geometric regularity, then we have a real mystery that demands an explanation beyond hand-waving about unusual conditions. Plasma physics provides the tools to diagnose these situations. You can model the expected plasma behavior around a comet, incorporate estimated solar wind parameters, and determine the magnetic field strengths needed to create the observed structures and compare those requirements to known natural sources. If the analysis shows that maintaining the observed geometry requires conditions that cannot plausibly exist in a natural cometary environment, you are left with two options. Either our models of plasma physics are incomplete, or Bialis is not relying on natural processes alone. The X pattern is particularly bothersome to physicists familiar with plasma confinement. Fourfold symmetry is common in engineered magnetic traps, where coils are arranged in quadrupole configurations. Nature rarely produces such clean symmetry without very specific forcing. You see it in crystals, where atomic lattices dictate the structure. You see it in some planetary magnetospheres where geometric effects from rotation and solar wind interaction create organized patterns. But in a cometary coma, far from any rotating body with a weak or non-existent internal magnetic field, obtaining an X pattern is very difficult to justify. With standard physics, we will know more in December. By then, the object will be far enough from the sun that imaging will not have to fight against solar glare. The geometry will be favorable for Northern Hemisphere observatories. High-resolution photometry and spectroscopy will either confirm the plasma structures are real and persistent, or show them to be observational artifacts specific to the difficult viewing conditions in October. Both answers are important. If they are artifacts, we learn about the limitations of our detection methods and the care needed when interpreting faint object imagery. If they are real, we are faced with something that challenges our understanding of how comets work, or forces us to seriously consider that Atlas may not be a comet. The phenomenon of its anti-tail stream becoming a true sunward tail. Comets are one of the most recognizable features in astronomy. They point away from the sun. They are always pulled by the solar wind and radiation pressure into long streams that can stretch for millions of kilometers into space. The physics is very simple. Sunlight carries momentum, and when photons strike the dust particles ejected from a comet, they transfer that momentum, pushing the particles away from the sun. The solar wind, a stream of charged particles flowing outward from the sun at speeds of hundreds of kilometers per second, does the same thing to the ionized gas. Both effects work in the same direction, away from the source of the radiation and wind, creating the classic comet tail. Sometimes you see two tails, a slightly curved dust tail, because the dust particles are massive enough for their orbital motion to matter, and a straight, often blue ion tail, which is made of ionized gas, reacting primarily to the solar wind's magnetic field. Both point away from the sun. This is fundamental to cometary behavior, so much so that it's one of the first things you learn in introductory astronomy. Tails always point away. Except when they don't, anti-tails, more properly called anti-solar point tails or sunward spikes, are rare but documented features where material appears to stream toward the sun rather than away from it. The name is a bit of a misnomer, as it's usually an optical illusion caused by perspective effects when viewing a comet from certain angles. It can make part of the tail seem to project forward. Imagine looking at a curved structure almost edge-on. The parts of the curve extending toward you look like they're pointing in the opposite direction from the parts extending away. The anti-solar point tail is a result of viewing geometry, not of actual sunward motion of material. Atlas showed something different. The Hubble Space Telescope imaged it on July 21st, capturing a high-resolution view of the coma and surrounding material. The image shows a distinct sunward spike, material extending from the nucleus in the direction of the sun. It was not a subtle perspective effect, but a clear, distinct structure with a projected length of about 2:1 in the image. But when Avolo and Ezekowitz corrected for the viewing angle, they calculated the three-dimensional length to be about 10:1. It's a stream, not an optical illusion. To create a stream of material directed toward the sun, you are fighting against radiation pressure and the solar wind, both of which want to push material away from the sun. You need a mechanism to overcome those forces. The explanation that Lowe and Quito offered in their September paper involves the specific properties of ice sublimation. When carbon dioxide ice on the comet's surface absorbs solar radiation, it sublimates, turning directly from a solid to a gas. This rapid expansion carries along embedded fragments of water ice, or those lying on top of the carbon dioxide ice. These ice particles, now detached from the surface, scatter sunlight, effectively creating the visible light we see as a gaseous shroud around the nucleus, the coma. But they also sublimate water ice. At the temperatures involved here, a few hundred Kelvin doesn't last long. These ice particles turn into gas themselves over timescales ranging from a few minutes to a few hours, depending on their size. If the sublimation ejects ice particles with significant velocity, and those particles begin to sublimate, immediately, they will create a stream of material moving away from the nucleus, but is continuously losing mass. The key lies in the timing. At a distance of 34 astronomical units from the sun, the sublimation of water ice creates a peak in the scattering cross-section. There is enough solar heating to sublimate the particles quickly, but not so much that they disappear immediately. That balance creates a region where the density of light-scattering ice particles is greatest. If that region of greatest density happens to be offset toward the sun relative to the nucleus, you get an anti-tail. Particles are moving outward in all directions from the comet, but the particles moving toward the sun will survive longer before completely sublimating compared to the particles moving away from the sun. That asymmetry in particle lifetime creates an apparent asymmetry in the brightness distribution, in a sense. This is still an optical effect, not actual motion toward the sun, but it's based on the real physics of how the rate of sublimation, and changes with heliocentric distance. That is a natural explanation for what the Hubble Space Telescope saw in July. It works mathematically. The model that Lovaquito published matches the elongation ratio and the observed brightness distribution. But it also predicts something specific as BAI-ALAS. BAI-ALAS-A continues to approach the sun, moving from 4 astronomical units inward to 2, then to perihelion at 1.356. The sublimation rate will change. Water ice particles ejected at closer distances will sublimate faster. The peak scattering region shifts. Eventually, the anti-tail structure will disappear, replaced by more symmetrical outgassing, and then potentially a traditional tail as refractory dust that is slow to sublimate begins to dominate the coma in September. New images from the Nordic Optical Telescope in the Canary Islands confirmed that prediction. The anti-tail had diminished. Instead, a faint tail stretched away from the sun, the normal configuration you would expect from a comet. David Gilbert and Ye Kwanji published an analysis in mid-October, documenting the transition with photometric measurements. showing the change in the geometry of the mass flow. This must have been a satisfying moment. Prediction made, tested, and confirmed. Natural cometary behavior explained by well-understood physics. The anti-tail was not evidence of technological propulsion or maneuvering. It was the physics of sublimation playing out exactly as theory suggested. Case closed. But this is where Adam Hibbard, one of Loeb's colleagues at Harvard University, asked an inconvenient question. If you were operating a spacecraft and wanted to decelerate on approach to a star system, you would fire your engines in the direction of travel, creating thrust opposite to your velocity. That's called a retrograde burn, in astronautical terms. The exhaust would flow out in front of the spacecraft, creating a visible plume pointing toward your destination. From the perspective of an outside observer, it would look exactly like an anti-tail, material stretching toward the sun, opposite to the expected direction. Then, when you finished your braking maneuver and need to adjust your trajectory for planetary encounters, you might reverse your thrust, firing the engines in the opposite direction to provide acceleration, or make course corrections. That exhaust would flow behind the spacecraft, creating a traditional tail-like structure. Again, from an observer's perspective, it would appear identical to what Atlas just did, an anti-tail in July and August, a transition phase in September, a normal tail in October, a disturbingly convenient temporal alignment if Bialis were a spacecraft executing a deceleration burn, followed by a perihelion maneuver. The transition sequence from anti-tail to tail would occur within the exact observed timescale. The total mass ejected was about 2 million tons according to the measurements. The integrated production rate represents about 0.00005% of the object's total mass. That is a surface layer about 4 centimeters thick if spread evenly over a sphere 5 kilometers in diameter. For a natural comet, 4 centimeters of erosion is negligible. Comets regularly lose meters of surface material during their perihelion passages. The amount lost tells us almost nothing about what lies beneath. For a spacecraft with a coating, designed to mimic cometary activity while shielding the internal systems from solar radiation, 4 centimeters is exactly what you would expect. Enough material to create convincing spectral signatures and visible activity, but not so much that you risk exposing the underlying structure. Loeb was careful to concede that the natural explanation for the jet reversal is perfectly adequate. The model by Quito and Loeb requires nothing exotic. It is standard thermodynamics and radiative transfer. The sublimation rate, particle sizes, and scattering properties are all within the normal range for cometary material. If you showed most planetary scientists these observations, without mentioning the other anomalies of 3IATLAS, they would agree that it is consistent with a comet transitioning from cold, distant activity, dominated by carbon dioxide, to warmer, closer activity, where inert dust becomes important. The problem is that the other anomalies do not disappear the orbital deviations, the brightness paradox, the geometric plasma patterns, the compositional anomalies like iron-free nickel, the extreme negative polarization, the orbital alignment with the ecliptic plane, and the timing of its close approach to multiple planets. Each piece has a natural explanation, but each natural explanation requires different special conditions: an unusual composition to explain the nickel, unusual dust properties to explain the polarization, an unusual magnetic field to explain the plasma geometry, and an unusual viewing geometry to explain the brightness. At some point, invoking multiple anomalous conditions independently becomes less parsimonious than considering a single explanation. That explains everything. If P-Atlas is technology, a probe or spacecraft rather than a natural comet, then all the anomalies resolve into expected behavior for an engineered system operating in an environment for which it was not originally designed. The composition reflects manufacturing processes rather than natural formation. The trajectory reflects deliberate navigation rather than gravitational freefall. Brightness management reflects operational priorities, like power generation or thermal control, rather than a simple thermodynamic response to solar heating. The plume orientations reflect propulsion system activity rather than asymmetric sublimation. This is the hypothesis that Adam Hibbert explored in his analysis, not claiming that it is definitively artificial, but pointing out that the artificial hypothesis removes the need for multiple layered coincidences. Occam's razor. The principle that simpler explanations are preferred usually favors natural interpretations. A rock is more likely than a spaceship. But Occam's razor also says that you should minimize the number of independent assumptions. One strange assumption that the object is technology versus 7 or 8 independent anomalous natural conditions changes the calculation. Post-perihelion observations will test this directly. If P-ATLAS is natural, it will continue to show comet-like evolution. The tail will brighten as new material is exposed to solar heating. The spectral signatures will remain consistent with an icy body composition. Activity will taper off as the object moves away from the sun and its temperature drops. All of this is predictable from thermodynamics. If it is artificial and the anti-tail was actually a braking burn, then the post-perihelion behavior might look different. Activity might drop off more sharply than expected if the propulsion system ceases operation after completing its maneuvers. The spectral signatures could change if a surface coating is depleted and the underlying material becomes visible. The brightness might stabilize at a level inconsistent with sublimation. Continuous sublimation of ice, any of which would be difficult to explain with natural cometary models, and there is also the possibility of secondary deployments. If the object were a mothership, as Loeb has speculated, perihelion would be the time to release smaller probes. The small spacecraft would be designed to intercept planets, asteroids, or other targets of interest. Those deployments would appear in photometry as sudden changes in brightness, or in astrometry as multiple distinct light sources where previously there was only one. High-cadence monitoring throughout November and December specifically looked for these signs. The tail flip itself does not prove anything. It is consistent with natural cometary behavior, but it is also consistent with spacecraft propulsion. The fact that both explanations work means we need more data to distinguish between them. The crucial observations will come in the next few weeks. Will the tail behavior continue to follow natural sublimation models? Will the object's trajectory remain purely gravitational, or show continued deviation? Will we see any evidence of fragments or secondary objects breaking away from the main body? Avolo has publicly stated that if Bialas behaves naturally throughout its perihelion pass and subsequent observations, he will downgrade its rating on his scale, down to a 2, meaning anomalous but probably natural. The anomalies would still be interesting, worthy of study, but not indicative of technology. However, if the post-perihelion data shows anything inconsistent with natural evolution, if the object continues to defy standard cometary models in a systematic way, then the technology hypothesis will become harder to dismiss. We are watching an experiment unfold in real time. Nature has given us an interstellar visitor with enough strangeness to raise questions, but not enough clear evidence to force a conclusion. The tail flip, the transition from anti-tail to tail, is one piece of that puzzle. If understood in isolation, it is unremarkable. If understood in the context of everything else Bialas has shown us, it becomes another data point in a pattern that refuses to settle into comfortable familiarity. By mid-December, when the object makes its closest approach to Earth, we will have months of post-perihelion observations. The tail behavior will be well documented, the trajectory thoroughly measured, and the spectral evolution carefully tracked. Or all that data will converge on natural cometary explanations, or it won't if it doesn't converge. If Bay-ATLAS continues to be systematically anomalous, in a way consistent with engineered behavior, then the conversation will shift from whether we should consider the technological hypothesis to what we are going to do about it. The International Asteroid Warning Network, IAWN, was established under the coordination of the United Nations in 2013, does not issue announcements lightly. The IAWN exists for one purpose: to detect, track, and characterize objects that could pose an impact threat to Earth. Near-Earth asteroids, comets on intersecting orbits, anything with even a small chance of impact, is flagged, analyzed, and monitored until its trajectory is fully understood. It is a global collaboration involving space agencies, observatories, and research institutions across dozens of countries. When the IAWN announces a campaign, it means something has triggered their threat assessment protocols. On October 21st, 2025, the same day DRAMASIC entered solar conjunction, the IAWN issued an editorial notice through the Minor Planet Center. The notice declared a coordinated observation campaign targeting DRAMASIC, running from November 27th to January 27th, 2026. This was the first time in the history of the IAWN that an interstellar object was designated for a planetary defense campaign. Read that again carefully: planetary defense, not scientific curiosity, not routine monitoring of an interesting visitor. Defense. The language in the announcement tried to be diplomatic, describing the campaign as an exercise to improve astrometric techniques for challenging targets like comets with extended comae and complex morphology. They framed it as a training opportunity, a chance for the global observation community to practice extracting precise positional measurements from difficult objects. But the subtext was impossible to miss. The IAWN does not organize 2-month-long campaigns. For objects that pose no threat, DRAMASIC will pass by Earth at a distance of 1.8 astronomical units, approximately 269 million kilometers, which is about 700 times farther than the Moon. There is no risk of collision, and the object's orbit is hyperbolic, meaning it is not even gravitationally bound to the Sun. It is just passing through and leaving. So why did the Planetary Defense Network mobilize? Resources usually reserved for potentially hazardous asteroids. The announcement mentions specific technical challenges. Comets present unique difficulties for astrometry because their comas and tails can pull the centroid measurements away from the nucleus's position. When you measure a comet's position, you're actually measuring the center of light, which can be offset from the physical nucleus by thousands of kilometers. If the outgassing is asymmetrical, which creates errors in orbital predictions. That makes sense. It is a real problem for tracking comets, but the IAWN had never organized a campaign to address this issue. They had tracked hundreds of comets over the years without the need for internationally coordinated efforts to improve measurement techniques. The timing was also revealing. The campaign began on November 27th, exactly 1 month after perihelion. That is when DRAMASIC would be far enough from the Sun for optimal observation, but still close enough to Earth for parallax measurements from different locations to provide a good baseline for determining its distance. The campaign ended on January 27th, allowing for 2 months of intensive tracking as the object moved out of the inner solar system. 2 months of coordinated observations involving dozens of facilities worldwide, all focused on a single object that posed no collision threat. The IAWN's announcement included another unusual element. They were requiring registration and workshop attendance for participation. If you wanted to join the campaign, you had to register by November 7th and attend a technical workshop on cometary astrometry techniques. Only participants who completed the workshop could contribute official observations and data sets. This level of scrutiny was unprecedented for IAWN campaigns. Usually, they welcome data from any qualified observer. The more telescopes tracking, the better the orbital solution. The restricted participation suggests they want to tightly control who contributes data. and how that data is analyzed. 3 days before IAWN's announcement on September 30th, Avalon had submitted a white paper to the United Nations in collaboration with colleagues Omayen, Dadi, and Gerson Tenenbaum. The paper, titled Advancing Interstellar Science, advocated for precisely what IAWN was now doing: coordinated global observation of interstellar objects to maximize coverage and ensure optimal scientific monitoring. Lau's argument in the white paper was direct. If interstellar visitors could potentially carry extraterrestrial technology, even with a low probability, the implications for humanity are significant enough that we should treat such objects with the utmost seriousness, similar to potential impact threats. The white paper used the term black swan event, situations with a small probability but enormous consequences. Standard risk assessment might dismiss low probability scenarios, but when the potential outcome includes first contact with extraterrestrial intelligence or worse, hostile technology entering our planetary system, the probability calculations change. You don't wait for certainty. You act out of precaution. IAWN's campaign was launched less than a month after that white paper reached United Nations committees, suggesting someone had taken that argument seriously. This created an interesting dynamic. Publicly, space agencies maintained that Atlas was a natural comet, exhibiting unusual but explainable characteristics. Official NASA statements stressed that there was no threat to Earth, and the object would pass through the solar system safely. Tom Stahl, NASA's lead scientist for small bodies, stated on the record that all data pointed to a cometary classification. The European Space Agency echoed this sentiment. Everything was routine, nothing to worry about. But behind that public messaging, IAWN, a United Nations-backed organization specifically tasked with planetary defense, was organizing the most comprehensive observation campaign ever directed at an interstellar object. They were doing it in the exact time frame, where, if the object intended to do something unexpected, it would become apparent. They are restricting participation to vetted observers, who have completed specialized training, and they are coordinating with international space agencies to ensure global coverage, meaning that wherever Baidu Atlas appears in the sky, multiple facilities will be tracking it simultaneously. The disconnect between public messaging and institutional behavior is stark. If Baidu Atlas were just an interesting but harmless comet, why mobilize planetary defense resources if there were even a small concern that it might be something else? Why downplay that possibility publicly, while privately increasing surveillance? One explanation is institutional caution. Without raising alarm, space agencies have learned from communication failures in the past that premature announcements create public panic, disproportionate to the actual risk. Remember the asteroid Apophis discovered in 2004, with initial impact probability calculations suggesting a small, but non-zero chance of impacting Earth in 2029. The media frenzy generated widespread concern, before refined observations showed the impact risk was essentially zero. The agencies don't want a repeat of that pattern. It's better to monitor intensively, gather definitive data, and only make public statements when the conclusions are certain. But that explanation assumes the risk is related to impact. Baidu Atlas is not going to hit Earth. The trajectory is clear on that point. So, what risk is IAWN concerned about? The campaign announcement does not say. It talks about improving astrometry techniques. It mentions the scientific value of studying rare interstellar visitors. It frames everything as an opportunity rather than a threat. Yet, the structure of the campaign, the resources being deployed, the level of coordination all suggest this is being treated as more than a scientific curiosity. Loeb's white paper presents a possibility that official channels will not. If Baidu Atlas releases secondary objects at perihelion, multiple probes or fragments separating from the main body, Those secondary objects could be on trajectories that bring them closer to Earth than the main object. Detecting and tracking those secondary objects requires coordinated observation with high-cadence monitoring. You need multiple tracking facilities so that if something breaks off, it is recorded immediately and continuously tracked until its trajectory is fully characterized. The IAWN campaign is designed for precisely that scenario. 2 months of intensive monitoring. Multiple observation sites provide redundant coverage, and standardized measurement techniques ensure all positional data is comparable. Workshop training ensures everyone knows how to distinguish real objects from artifacts or noise. It is a deployment protocol to detect and track unexpected secondary objects. Another aspect, rarely discussed publicly, is the possibility of a post-perihelion trajectory change if ATLAS performs maneuvers while it is obscured by the sun. Those maneuvers could divert it closer to Earth than is currently predicted. The probability is low, but if you are assessing a threat, you do not ignore low-probability scenarios with high-consequence outcomes. Intensive object tracking. Immediately, post-perihelion allows you to detect trajectory changes within days instead of weeks, providing maximum warning time if the approach distance begins to decrease. The involvement of the IWN also signals something about the internal discussions at the governmental level. The organization reports to the United Nations Committee on the Peaceful Uses of Outer Space for them to approve and provide resources for this campaign. There had to be briefings, presentations, and consensus among member states that the monitoring was justified. Whatever data or analysis convinced those committees has not been made public. We see the output, the campaign itself, but not the input, the evidence or arguments that drove the decision. There is a precedent for this type of monitoring. When asteroid 2012 TC4 made a close approach to Earth in October 2017, passing within 44,000 kilometers. The IWN coordinated an observation campaign, and that campaign had a clear purpose. The asteroid was newly discovered with an uncertain orbit. Close approaches provide excellent opportunities to refine orbital parameters and assess future impact risks. 2012 TC4 might return someday, on a more threatening path. So, collecting data during the 2017 pass was valuable. The operation with ATLAS is different. It will not return from its hyperbolic orbit, which means this is a one-time visit. After it leaves the inner solar system in early 2026, it will never return. In 50,000 years it will be several light-years away, traveling through interstellar space towards an unknown destination. So the IAWN campaign is not about assessing a future threat. It is about understanding what is happening right now during this single pass. Its passage through our neighborhood adds another layer to the workshop's mandate. What techniques are they teaching? Standard astrometry is well established. Measuring a comet's position is fundamentally no different from measuring an asteroid's position. You account for the extended coma by adjusting models for the brightness distribution and extracting the nucleus's position, which is routine work. What specific training do observers need that isn't already standard practice? One possibility is the detection of faint companion objects. If secondary bodies break off from Borealis, they would be much fainter than the primary object. Standard comet observation techniques, optimized for the bright central region, are challenged when detecting faint nearby objects. This requires different processing procedures, different exposure times, and different analysis methods. The workshop might be training observers in those techniques, preparing them to search for things that are usually not visible in conventional comet images. Another possibility is rapid response protocols. Should something unexpected appear, IAWN would want immediate notification, not delayed reports. Through the usual scientific channels, the workshop could be establishing communication procedures, how to contact IAWN, what information to include, and how to format the data. Building that network before the campaign begins ensures that if something noteworthy happens, the response is coordinated, not chaotic. The campaign also serves a diplomatic function. By involving observatories from many nations, IAWN ensures that the data is not controlled by a single country or agency. If discoveries are made, they are immediately international, shared among all participants. This prevents scenarios in which one country monopolizes information about something potentially important. That is transparency through collaboration, ensuring that no one can claim secret knowledge or conceal important findings. To the public, the IWN campaign sends a mixed message. On one hand, it is reassuring that serious organizations are monitoring DRAMASIC carefully. If there is a genuine concern about a threat, we want planetary defense systems to be engaged in tracking it. On the other hand, the very fact that they are involved raises the question of why. What do they know or suspect that justifies this level of attention? The answer is likely more mundane than conspiracy theories might suggest. DRAMASIC is genuinely unusual, a combination of anomalies that, whatever their ultimate explanation, merits close observation. The IWN seizing the opportunity to practice coordinated surveillance is operationally sound. When a real threat does emerge one day, having trained international teams, experienced in rapid campaign deployment will be invaluable. DRAMASIC, threat or not, provides that training opportunity. But training exercises are usually announced as such, and the language the IWN is using, the structure of the campaign, the restricted participation, all suggest this is more than practice. It is operational. They are treating DRAMASIC as something that requires active monitoring under protocols, usually reserved for objects of concern. November 27th is when the campaign officially begins. Between now and then, DRAMASIC completes its perihelion passage, emerges from solar conjunction and becomes observable again. The first campaign observations will document the object's post-perihelion state. That initial dataset becomes the baseline for everything that follows. If the object shows changes from its pre-perihelion observations, differences in brightness, spectrum, morphology, or trajectory, those changes will appear immediately in the data. The IWN campaign is positioning dozens of telescopes to watch the reveal. They are coordinating schedules to ensure continuous coverage. They are training observers to look for specific signatures that might indicate something beyond normal cometary evolution, and they are doing all of this within a formal framework, in the language of planetary defense, meaning they considered BA and Atlas relevant to the safety of Earth, even though its orbit posed no risk of collision. What they knew that we did not remains unclear. What they suspected but would not say publicly was easier to infer, and what they would find when intensive monitoring began in late November might finally answer the question that had been growing since July. Are we looking at the most unusual comet in history, or are we looking at something else entirely? On August 15th, 1977, the Big Ear Radio Telescope at Ohio State University was running its routine sky scan, searching for patterns in radio emissions that might indicate something other than natural cosmic noise. The telescope was not looking for anything in particular. It was part of the search for extraterrestrial intelligence effort, SETI, which systematically monitored radio frequencies, in the hope that somewhere, something might be transmitting. At 10:16 p.m. Eastern Time, the telescope detected a signal at 1,420 megahertz. That frequency is right in the middle of the hydrogen line, the radio emission from neutral hydrogen atoms that floods the galaxy. It is a natural choice for interstellar communication, because hydrogen is the most abundant element in the universe, and any technological civilization would be well aware of that frequency. The signal lasted for 72 seconds. precisely the time it took for the Big Ear's beam to sweep across a fixed point in the sky as the Earth rotated. Jason reviewed the computer printout a few days later and saw the spike in signal intensity, much stronger than the background noise, so much so that it stood out immediately. He circled the alphanumeric sequence 6EQUJ5 and wrote in the margin. That annotation gave the signal its name, the wow signal. Nearly 55 years later, it remains one of the most compelling detections in the history of SETI. No explanation has ever fully accounted for it. No subsequent observation has ever detected it again, despite decades of follow-up surveys. The signal's origin was traced to a region in the constellation of Sagittarius. Right ascension 19 hours and 25 minutes. Declination 27 degrees. That is not a point in space. It is a direction. Looking at those coordinates, you are staring toward the center of the Milky Way galaxy, through dense star fields and obscuring molecular clouds. Direct views into the galactic core. Tens of thousands of stars lay within the antenna's beam. The Big Ear was pointed at that location, identifying which exact star, if any, emitted the signal was impossible without further detections. Fast forward to the year 2025. 3IATLAS appears in our solar system and is the third confirmed interstellar visitor we have ever detected. Its trajectory traced back through space, pointing to an origin in Sagittarius, not the exact same coordinates as the wow signal. That would have been too perfect. But it was within 9 degrees. 9 degrees on the celestial sphere represents a vast area when you are talking about interstellar distances. But directionally, it is close enough that Avalon calculated the probability of a random alignment at about 0.6%. That number matters. 0.6% is not incredibly rare. It is not lottery-winning odds, but it is unusual enough that when you combine it with 3IATLAS's other statistical anomalies, the cumulative probability drops into the range, making randomness difficult to defend. Multiply 0.6% by the 0.2% chance of ecliptic alignment, by the 0.005% chance of planetary approach timing alignment, by various compositional and behavioral anomalies, and you quickly arrive at probabilities, measured in parts per quadrillion. Loeb's analysis goes further. If the wow signal originated from 3IATLAS in 1977, what would that require? First, where was the object in 1977 tracing its trajectory back at 58 kilometers per second? Accounting for gravitational influence from the Sun and planets puts it at about 600 astronomical units. From Earth in August 1977, that is about 90 billion kilometers, deep in the outer solar system, beyond the Kuiper belt, but still technically within the Sun's gravitational influence. At that distance, transmitting a signal detectable by the Big Ear would require between 0.5 gigawatt and 2 gigawatts of power, depending on antenna gain and beam focus. That is comparable to a large nuclear power plant on Earth. Not impossible for an advanced civilization, but not trivial either. You do not accidentally broadcast at those power levels, unless you have a good reason. The signal was also blue-shifted by about 10 kilometers per second, meaning the source was moving toward Earth. 3IATLAS is currently moving toward the Sun and outward, was moving in the general direction of Earth. In 1977, the Doppler shift wasn't a perfect match, because measuring the precise velocity from a single 72-second signal is difficult. But within the range of uncertainty, it was consistent. This is where the speculation becomes both tantalizing and frustrating. If an Atlas flyby transmitted the wow signal, what if it was meant to be a radar pulse, not a communication attempt? An active sensor sweep, searching for planetary bodies in the inner solar system. You are approaching a star system from interstellar space. Then, knowing where the planets are has operational value. You cannot see them with the naked eye, from hundreds of astronomical units away. They are too faint, lost in the glare of the star. But if you transmit a powerful radar pulse and listen for the reflections, you can detect large objects and characterize their orbits. Earth would reflect a tiny fraction of that pulse. Venus would reflect a little. Jupiter, despite being further from the transmission point in 1977, would reflect more because of its immense size. By analyzing the timing and intensity of those reflections, if you are patient enough to wait for the round-trip travel time, you could map the inner solar system's architecture. You would know where to aim your trajectory for optimal planetary encounters decades later when you finally arrive. The problem with this hypothesis is verification. We have a single detection of a 72-second signal that has never repeated. Radio SETI has pointed telescopes back at that region of Sagittarius hundreds of times over many decades. Modern instruments are far more sensitive than the Big Ear was, and have listened across wider frequency bands, and for longer integration times. Nothing. The WOW signal remains unique, a singular event. No follow-up, no confirmation, no additional data. That uniqueness is either evidence against the signal being a genuine extraterrestrial communication, or it is evidence that it was a targeted transmission, not intended to be repeated. If you are sending a radar pulse to map a star system, you do it once and move on. Continuous transmission is a waste of energy. The argument cuts both ways. Skeptics say that the lack of repetition suggests the WOW signal was an instrumental error, or terrestrial interference, or some transient natural phenomena. Proponents say that directed transmissions would not necessarily repeat, and that expecting them to is anthropocentric thinking, based on how we conduct radio astronomy. The arrival of B.A. Elias from the same direction approximately 48 years later adds weight to the Zeta hypothesis. Without proving it, coincidences happen. Sagittarius is a rich region of the sky. It is where the galactic center lies, where star density is highest from our perspective, where molecular clouds and stellar nurseries create a complex radio background. An interstellar object coming from that direction, and a mysterious radio signal originating from that direction could be completely unrelated. But the timing is unsettling. If B.A. Elias left its system of origin a few million years ago, which seems plausible given the distances and velocities involved, it has been approaching our solar system throughout modern human history. The moment it was 600 astronomical units away. The 1970s coincided with humanity's first serious efforts. At Radio SETI, we began listening just as a probe. Hypothetically would be close enough for radar scans of the inner system to become useful. That synchronicity is what bothers people. Either it is the most remarkable coincidence in SETI history, or it is not a coincidence. If it is not a coincidence, the implication is that something has been approaching our solar system for millions of years, and right around the time it got close enough to begin active sensing, we happened to develop the technology to detect those transmissions. The odds of that seem incredibly low, unless there is some causal connection we are missing. One possibility is that the timing is not actually remarkable. Human radio technology has only existed for about a century. Radio SETI specifically has been active for about 65 years. If interstellar probes are common, and they approach star systems regularly throughout the galaxy, then the probability that one would arrive during the window of humanity's brief radio capability is not astronomically small. It is just rare on a human timescale. We notice it because we are the ones experiencing it, but cosmically it is business as usual. Another possibility involves observer selection effects. We can only detect a signal during the time we are listening. If the probes continuously approach star systems but only transmit when they are within a certain distance threshold, we would only detect them. If we happen to be listening during that window of approach, the vast majority of probes would go undetected, because they arrived before we developed radio astronomy, or will arrive after our civilization has ended. The ones we do detect necessarily must correlate with the phase of our technological capability. These anthropic arguments dissolve the coincidence without requiring conspiracy or intention. They are philosophically satisfying, but don't really advance our understanding of what DRAMASIC is, or whether the WOW signal connection is meaningful. What would make the connection meaningful? The detection of new transmissions. If DRAMASIC emits radio signals as it passes through the inner solar system, signals that we could detect and analyze, that would transform the hypothesis from speculation into testable science. To date, no radio telescope has reported detecting transmissions from DRAMASIC. That is not surprising if it is a comet. Comets are radio quiet, except for very faint emissions from their comas, requiring sensitive instruments to detect. But here's the gap. Major radio observatories have not systematically monitored DRAMASIC. SETI programs don't typically point their dishes at comets. Why would they? Comets are natural objects. You aim SETI telescopes at stars, planetary systems, regions of space, where you might reasonably find technological civilizations, not at chunks of ice. Passing through your own solar system, Loeb has called for directed radio observations of 3IATLAS, arguing that the accumulated anomalies justify treating it as a SETI target, regardless of how unlikely the technological hypothesis may seem. Point your dish. Listen on the hydrogen line frequency and neighboring bands. See if anything shows up besides noise. The cost is minimal. A few hours of telescope time. The potential benefit if something is detected is enormous. However, as of late October, no major facility has announced plans to conduct such observations. Part of the resistance comes from the institutional conservatism of SETI, which operates on a limited budget. With competing proposals for telescope time, pointing at Pallas means not pointing at more traditional targets, which have better theoretical justification for potentially containing detectable signals. If an observation yields nothing, which is the expected outcome, that is telescope time, spent with zero scientific return. Proposal reviewers are understandably reluctant to approve what looks like a long shot. But there is also a more subtle problem. If you point a radio telescope at Pallas and detect a signal, you have just created a major problem. First contact protocols require verification, international coordination, and careful analysis before public announcement. The discoverer becomes responsible for managing what could be the most consequential observation in human history. Most scientists prefer not to put themselves in that position, especially when the probability seems low. So we are left with a tantalizing connection that cannot be confirmed or ruled out without the observations that no one is making. The WOW signal occurred, and Pallas was coming from the same direction about 48 years later. The calculation for a radar transmission from the object's 1977 position works out. The Doppler shift is consistent. The timing of an active scan versus arrival in the inner system aligns with what you would expect from a designed mission profile. To explore a planetary system, but without new detections, it remains a suggestive but inconclusive situation, a pattern that could be meaningful. Or it could be the kind of false pattern that humans excel at finding. In random data, we see faces in clouds. We see constellations in random star distributions. We see connections between events separated by decades, because our brains are wired to find cause even where only correlation exists. The scientific response is to gather more data, to monitor Pallas with radio telescopes, to analyze its orbit for any deviations that might indicate navigation intentionally toward Earth's orbit or planetary approaches, and to look for secondary signals or possible transmissions as it passes perihelion or approaches Earth in December, recording everything and allowing the evidence to accumulate. until the patterns either resolve into clear, natural explanations, or into something that requires us to reconsider what we think we are looking at. November and December will be crucial for this, as the object becomes easily observable again post-perihelion. Any research team with access to radio telescope time could, in principle, carry out observations. Whether or not they do so depends on funding, proposal approval, and the willingness to dedicate resources to what most consider a target of low probability. But the window is limited. By February, DRAMASIC will be moving back into the outer solar system, fading from view, and the opportunity to directly test the wow signal hypothesis will be gone. If transmissions are detected, everything changes. The conversation shifts from whether DRAMASIC is anomalous to what we will do about a confirmed intelligent technology operating in our solar system. If no transmissions are detected, the connection remains speculative, an interesting coincidence that generates papers and discussion, but does not fundamentally change our understanding. Either way, the wow signal reminds us that the universe has given us an event that is unexplained and tantalizingly looks like contact. DRAMASIC arriving from the same direction decades later could be a coincidence, or it could be the universe giving us a chance to connect the dots, to see a pattern spanning nearly 55 years and reveal something profound about our place in the universe. We just need to be willing to look. 8D. Twin often looks flat. Row 4. Avi Loeb developed his scale for interstellar objects, specifically because DRAMASIC demanded it. Before this object appeared, the theoretical framework did not exist. There was no standardized way to quantify the level of anomaly of an interstellar visitor. No metric to assess technological probability. Loeb created a 10-point scale, where 0 represents certainly natural, a 10 represents certainly artificial, and the ranges in between capture varying degrees of anomaly and uncertainty. DRAMASIC currently ranks at a 4. That was not a guess or an intuition. It was a calculation based on 8 specific anomalies. Each anomaly was assigned a probability of occurring naturally, and by multiplying those probabilities together, you get a cumulative likelihood that measures how expected or unexpected the object's characteristics are, if it were formed through natural processes. The result places it firmly in a region of uncertainty, too strange to be dismissed as normal, but not definitively artificial. The first anomaly was the orbital alignment, meaning DRAMASIC approached the Sun in a single plane. The orbit was inclined only 5 degrees relative to the ecliptic plane, and the ecliptic plane is not a physical structure. It is the plane defined by Earth's orbit, and by extension, the approximate plane, where most of the solar system's planets orbit. It exists because the solar system formed from a disk of rotating gas and dust, and the conservation of angular momentum keeps everything spinning. In roughly the same plane, interstellar objects have no connection to that plane. They form in other star systems with their own unique orientations. When they are ejected into interstellar space, their trajectories are randomized by gravitational interactions. Some travel prograde, matching the rotation of their parent system. Others travel retrograde, with inclinations spanning the full range from 0 to 90 degrees, without any preference for a particular value. For DRAMASIC to arrive aligned within 5 degrees of our ecliptic plane by pure chance requires a specific geometry. Out of all possible approach vectors from interstellar space, only about 2% are aligned that closely. It is not impossible, 2 in 100, but it is the first statistical oddity. If you were designing a mission to explore a system of planets efficiently, you would choose an orbit in the ecliptic plane, because approaching planets from there requires the least amount of fuel. Starting from a high inclination forces costly plane change maneuvers. The 5-degree alignment is optimal for approach, suspicious for a natural arrival. The second anomaly was the timing of the planetary encounters. DRAMASIC passed within tens of millions of kilometers of Mars in early October, Venus in early November, and Jupiter in March of 2026. Close approaches to multiple planets in a single pass are rare. Most interstellar objects either miss everything or happen to encounter one body. The probability of arriving at just the right time to pass close to 3 major planets is about 0.005%, 5 in 100,000. Once again, not impossible, but combined with the orbital alignment, you now have 2 unusual conditions occurring simultaneously. The product of 2% and 0.005% is 0.01%. 1 in 10,000, we are in lottery-winning odds territory, and we have only mentioned 2 anomalies. The third anomaly is mass. The third, Atlas, is very large compared to other interstellar visitors. Oumuamua was first discovered in 2017. Perhaps a few hundred meters wide with an estimated mass of tens of thousands of tons. Hyperion. The second visitor in 2019 was slightly larger, but was still measured in the low millions of tons. The third, Atlas, with a minimum diameter of 5 kilometers, with a mass exceeding 33 billion tons, is thousands to millions of times heavier than both its predecessors. It also moved faster than Oumuamua, entering at about 26 kilometers per second, with a hyperbolic excess velocity upon entry of 32 kilometers per second. The third, Atlas, arrived at 58 kilometers per second. Not only did it have greater mass, it also carried more kinetic energy by a large margin. The combination of extreme mass and high velocity is unusual. Most large interstellar objects would be gravitationally bound to their parent stars. Only rare ejection events create large objects with high velocities. The probability of detecting one in the brief window, when humanity has the technology to identify interstellar visitors, is much lower than 1%. The fourth anomaly is composition, specifically the nickel emission. Spectroscopic analysis from the Keck Observatory in August showed prominent nickel emission lines. Without corresponding iron lines, that ratio is wrong for natural objects. Nickel and iron are sister elements formed together in stellar nucleosynthesis and are found in similar ratios throughout the universe. Rocky bodies, asteroids, comets all show iron along with nickel when you analyze their spectra. Industrially produced nickel alloys on Earth intentionally concentrate nickel while minimizing iron for the useful properties of stainless steel alloys. Superalloys for jet engines. Corrosion-resistant materials all use a high nickel, low iron composition. Finding that signature in a comet is like finding refined aluminum in a meteorite, technically. It is possible if some strange natural process creates extreme chemical fractionation, but so rare that the probability is less than 1%. The fifth anomaly is the water content. Measurements from the James Webb Space Telescope showed that Bialus had only 4% water by mass in its outgassing. Most comets are predominantly water ice, with smaller amounts of carbon dioxide, carbon monosulfide, and other volatiles. Solar system comets typically show water making up 70 to 90% of their outgassing, even accounting for compositional variations and different formation environments. 4% is extremely low. Carbon oxides dominated instead, making up 87% of the observed volatiles. That inverted ratio suggests the object either formed in an extremely cold environment, where carbon oxide ices were more abundant than water ice, or the surface we are observing was depleted of water while retaining its carbon oxides. Both explanations work, but they require specific conditions. The probability of encountering an interstellar comet with such an unusual composition is difficult to quantify precisely, but it is likely less than 5%. The sixth anomaly was its polarization. Observations from the Very Large Telescope in September showed extreme negative polarization, meaning the light scattered from the coma had a wave orientation parallel to the scattering plane rather than perpendicular. This behavior is almost unprecedented in comets. The dust particle size distribution and composition required to produce it are very specific. Natural cometary dust tends to have a wide range of sizes and a mixed composition, which produces positive polarization in most cases. Laboratory experiments can produce negative polarization with carefully controlled particle sizes, typically in the sub-micrometer to micrometer range, and specific refractive indices, finding those exact conditions in a natural cometary coma, where dust is constantly being generated and ejected with various sizes, is extremely unlikely. The VLT team estimated the probability at less than 1%. The seventh anomaly was the lack of non-gravitational acceleration, despite visible outgassing. Richard Quaid, Peter Feeve, and Avalon analyzed over 4,000 positional measurements from 227 observatories worldwide, spanning from mid-May to late September. They found no detectable deviation from purely gravitational motion. The residuals in right ascension, eccentricity, and inclination are consistent with zero, which sounds like it should be normal. Gravity governs orbital motion, but for active comets, it is not unusual for the comet to outgas. The vapor jets create a recoil force that pushes the nucleus slightly off its gravitational path. These non-gravitational accelerations are well documented and frequently measured. For solar system comets, the magnitude depends on the comet's mass and the intensity of the outgassing. Small, active comets show large deviations. Large comets show smaller deviations, but they are still detectable. DRAMASIC was outgassing strongly, losing 25 kilograms per second, according to F's observations. That should produce a measurable recoil force. Yet, the fact that no deviation was detected means either the outgassing was perfectly symmetrical, so the forces canceled each other out, or the object's mass was so large that the recoil force was below the detection threshold. Perfectly symmetrical outgassing is inconsistent with the observed anti-tail, and the geometric plasma models indicate asymmetry. Therefore, the object must be extremely massive, working backward from the detection limits. The analysis concluded that DRAMASIC must weigh at least 33 billion tons. That is about 1,000 times more massive than Hyperion, despite being only a few times larger in diameter. The implied density is much higher than that of typical comets, which are rubble piles, loosely bound together with a lot of empty space. The high density suggests that the object is either more rock than ice, or it has a non-porous internal structure unlike typical comets. The eighth anomaly returns to the alignment of the wow signal. A 9-degree directional match with a 0.6% chance probability. By itself, this is the weakest anomaly. 9 degrees is a large cone of uncertainty in space, but in the context of the other 7 anomalies, it adds another layer of statistical improbability, multiplying all 8 probabilities together 2% for the orbital alignment, 0.005% for the timing of the planetary approach, under 0.1% for the combination of mass and velocity, under 1% for the iron-nickel ratio, under 5% for the low-water composition, under 1% for the extreme polarization, under 1% for the extreme density implied by the lack of acceleration, non-gravitational, 0.6% for the wow signal alignment. The cumulative probability is absurdly small, parts per quadrillion, and his colleagues calculated the exact value to be less than 1 in 10 to the 16th power. That is 1 in 10 quadrillion. In other words, if you were to observe 10 quadrillion random interstellar objects, you would expect to see one object with this combination. of these characteristics purely by chance. Now, there's a statistical trap here. After the fact, you can make anything seem improbable if you carefully choose which characteristics to measure and which probabilities to multiply. You can create odds that seem impossible for any object. This is known as the sharpshooter fallacy, where you shoot bullets into a barn wall and then draw targets around the holes to make it look like you hit the bullseye. The rebuttal to that fallacy is to define your criteria beforehand and apply them consistently. Loeb's scale attempts to do just that. The 8 anomalies were not cherry-picked. After they were found to be unusual, they are the kind of parameters you would naturally check for any interstellar visitor trajectory. Mass, composition, behavior. These are the basic observables. The fact is that they all happen to fall in the anomalous tail end of the distribution of their probabilities. It is not a case of cherry-picking convenient events. It is the object itself being consistently strange across independent measurements. That is why DRAMASIC ranks at a 4 on the scale. It is not one strange characteristic. It could be a fluke. It is 8 independent characteristics, all pushing toward the low probability end. Natural explanations exist for each characteristic in isolation, but explaining all of them simultaneously requires a combination of multiple rare conditions. This becomes less parsimonious than considering a single alternative explanation. The alternative is that DRAMASIC is artificial, a probe, a spacecraft or some other technological construct sent from another star system to explore our system. If that is true, all 8 anomalies are resolved into expected features. The orbital alignment is intentional navigation. The timing of its planetary approach is mission planning. The extreme mass and velocity are propulsion system capabilities. The iron-nickel ratio is materials engineering. The low water content is a thin surface layer mimicking stellar activity, comet-like, while protecting the systems underneath it. Extreme polarization and its surface coating properties. The lack of non-gravitational acceleration. The structural integrity of a solid manufactured object. The signal alignment is the shift in position from 48 years ago in the process of approaching a hypothesis. 8 predictions were confirmed, which is how Occam's razor is supposed to work. The simplest explanation, meaning the one with the fewest independent assumptions, is preferred. 8 separate and unusual natural conditions versus 1 strange artificial origin. The artificial hypothesis is simpler in that sense, although it sounds more extraordinary. But extraordinary claims require extraordinary evidence. Statistical anomalies, no matter how improbable, are not the same as physical evidence. We need observations that cannot be explained naturally, even in principle. Radio transmissions, resolved surface structures that show manufactured features, orbital changes that cannot be the result of outgassing or radiation pressure. The active deployment of secondary objects, something that definitively breaks the ambiguity. A rating of 4 means it is uncertain. It could be natural. It could be artificial. The data does not compel a conclusion either way. If the post-perihelion observations show continued natural cometary behavior, the rating would drop to 2, meaning anomalous but probably natural. If observations show behavior that is naturally impossible, controlled maneuvers, clear technosignatures, the rating would jump to 10. We are in the middle, suspended between mundane and profound explanations. The 8 anomalies warrant its remarkable nature. Whether it is remarkable for being the strangest comet we have ever seen, or remarkable for being our first contact with extraterrestrial technology, depends on data we do not yet have. The December observations will push the rating in one direction, or the other. Until then, a rating of 4 is where it sits, a number that says we truly do not know what we are looking at, and that uncertainty is very important. Brandon Bigger had no intention of becoming known as the prophet who predicted the assassination attempt on Trump But in April of 2024, a few months before the July 13th shooting at a rally in Pennsylvania, Bicker recorded a video describing a vision in which he saw a bullet fly past Donald Trump's ear, so close that it ruptured his eardrum. He described chaos, blood, and Trump surviving but being injured when the actual attempt occurred in July. Matching those details with eerie accuracy, Bicker went from an obscure Christian pastor to an overnight viral phenomenon. That feat, an incredibly specific prophecy that came true, gave his subsequent visions a weight they might not otherwise have had. When someone correctly predicts something so uncertain in such detail, you pay attention to what they say next, even if you are skeptical of prophetic claims. In general, what Bicker said next in a video, released in mid-October, was about aliens, specifically about a giant mothership coming to Earth. In his vision, Bicker described seeing a massive alien spacecraft flying over the Vatican and the Mayan temples in Mexico. Not two ships, but one. He emphasized that detail. He asked in the vision if there were multiple ships, and was told no, just one giant vessel. The ship moved slowly over the ocean in full view. Everyone saw it. It was broadcast on worldwide television, creating global panic. Then, smaller ships emerged from the mothership. Bicker described them as orbs of light, small vessels detaching from the main ship. The timing of this video, released in mid-October, as Bay Atlas approached perihelion, triggered immediate online speculation. Social media erupted with theories connecting Bicker's vision to the interstellar object, and forums lit up with discussions comparing his description of a mothership releasing smaller probes, with Loeb's hypothesis that Bay Atlas, if artificial, could potentially deploy smaller craft at perihelion. The parallel was striking. Bicker spoke of a large ship releasing many smaller objects. Loeb spoke of a mothership scenario where Bay Atlas, if artificial, would release small probes during its closest approach to the Sun. Bicker had actually mentioned this vision earlier in July, right after Bay Atlas was discovered. He described seeing small ships emerge from a larger one, spheres of light rising from something enormous. At the time, most viewers interpreted it as generic prophetic imagery, the kind of vague apocalyptic scenario common in religious visions. But the July timing, just as Atlas entered public consciousness, and the emphasis on October right before perihelion, created a narrative arc that conspiracy communities found impossible to ignore. The theological framework Big G used is important context. He did not claim these were benevolent extraterrestrial visitors. He explicitly framed them as demonic entities, spiritual forces using physical manifestation to deceive humanity. In his interpretation, the mothership and the smaller craft were a satanic deception, part of a larger end-time scenario preparing the world to accept the Antichrist. The beings were not aliens in the science fiction sense. They were fallen angels or demons taking on forms that a modern secular society would interpret as extraterrestrial. This theological lens does not make his prophecies any less interesting from a phenomenological perspective. If you strip away the spiritual interpretation and look only at the claimed observations, the flying objects, the mothership releasing smaller craft, the global visibility, the television coverage, you are left with descriptions that could apply to physical phenomena regardless of their ultimate nature or origin. Whether you interpret those phenomena as technology from another star system, or as the manifestation of spiritual entities, becomes a matter of worldview. The Internet did what the Internet does. Within a few hours, after Big G's October video circulated, edited versions appeared, linking his claims directly to Atlas. Some added images of the object from Hubble and the JWST. Others overlaid orbital diagrams showing its trajectory. The synthesis created a narrative where a Christian prophet and a Harvard astrophysicist were independently describing the same event from different conceptual frameworks. Loeb spoke of orbital maneuvers and the deployment of small probes. Big G spoke of a mothership and spheres of light. The vocabulary was different, but the core scenario aligned, a connection the mainstream media largely ignored. Prophetic visions do not make for comfortable material for the scientific press, but alternative media, conspiracy-focused platforms, and religious communities have amplified it powerfully to certain audiences. The combination of Big Girl's credibility from the Cham prophecy plus the scientific anomalies surrounding DRAMASIC created a perfect storm of confirmation this was a spiritual warning, confirmed by empirical observation, or depending on your perspective. This was interesting astronomical data being wrapped in apocalyptic religious interpretation. The detail of the orbs of light was particularly interesting, because it echoed descriptions from UAP encounters, unidentified aerial phenomena, UAP reports, especially from military personnel, frequently describe luminous orbs moving in ways inconsistent with known aircraft. These don't necessarily have to be connected to DRAMASIC, but the descriptive overlap between Big Girl's visions and existing UAP reports added a layer of cross-confirmation for those inclined to see connections. Skeptics point out that prophetic visions are inherently unfalsifiable if they haven't happened or don't happen. Big Girl could describe anything, and if it doesn't come to pass, supporters will argue that the timeline was misinterpreted, or that the prophecy was conditional on human response. If something vaguely matching the description occurs, it's counted as a hit, even if the details are loose. The Cham assassination prophecy was the exception, specific enough and accurate enough that explaining it away requires uncomfortable contortions. But one correct prophecy doesn't validate all subsequent claims. There's also the matter of influence. Big Girl had internet access. He followed the news. By October, DRAMASIC was headline material. Loeb's mothership hypothesis was being discussed in major publications. Big Girl could have absorbed that information either consciously or unconsciously, and incorporated it into his religious framework. No, vision and imagination are difficult to distinguish, especially when both draw from the same information environment. Claiming divine revelation for something you've read, even if you don't consciously remember reading it, is a well-documented psychological phenomenon. But then there is the mention of July, when Big Girl described the ships and orbs of light returning, when 3IATLAS was virtually unknown outside of expert circles. Loeb had not yet published the detailed papers on the technological hypothesis. The mothership scenario was not mainstream discussion. If Bicker was unconsciously pulling from the media, what media existed in early July that would have planted those specific images? The object had just been discovered, and initial reports called it a comet. Interesting for being interstellar but not yet laden with discussions of anomalies, or technological speculation. The timing is the issue, which is why some people take Big Girl more seriously. Either there is something to it, or he was lucky in guessing that an interstellar object would become associated with mothership theories. Or we have a genuine insight, through whatever process created his visions, psychological, spiritual, or otherwise. The detailed prophecy makes the lucky guess harder to accept, as an explanation from a sociological perspective. Bigfoot represents something important, regardless of prophetic accuracy. He is a conduit through which scientific uncertainties are translated into religious narrative. By alas, with its statistical anomalies and technological hypotheses, creates space for apocalyptic interpretation. Those looking for signs of the end times see a mysterious object from the stars, possibly dropping probes into our solar system, as exactly the kind of event that would precede major prophetic fulfillments, the beast system, a one-world government, the revelation of hidden truths. All the classic eschatological themes find purchase in interstellar visitor scenarios. This is not new. Every major astronomical event in history has been interpreted through religious frameworks. Comets were omens in antiquity. and eclipses signaled divine displeasure. Modern UFO phenomena are absorbed into both secular and religious explanatory systems. 3IATLAS is just the latest celestial appearance being pulled into those interpretive structures, amplified by social media and the real scientific puzzles the object presents. What makes this case unusual is the convergence. You have a prophet with a proven track record from a recent, specific prophecy. You have a scientific hypothesis from a respected astrophysicist, using mothership terminology. You have a temporal synchronicity, where the visionary details align with a perihelion window when a deployment would theoretically occur. And you have a real object anomalous enough that even skeptical scientists admit it deserves serious attention. That convergence proves nothing about the prophecy, or an alien visitation or a spiritual manifestation. It proves that when reality becomes strange enough, multiple explanatory frameworks begin to point at the same phenomenon. Scientists say probe deployment. Prophets say demonic manifestation. Both could be wrong. Both could be partially right, in ways that are not mutually exclusive. The technology of an advanced civilization would look like magic to less advanced observers. Clarke's third law: any sufficiently advanced technology is indistinguishable from supernatural phenomena. If Atlas were to release objects at perihelion, if we were to observe secondary craft emerging from the main object, how would different communities interpret that scientists would analyze trajectories, spectroscopy, biosignatures? They would try to determine its origin, purpose, and capabilities. Religious communities would see the fulfillment of prophecy, evidence of spiritual warfare, signs of the coming end times. Both interpretations would be internally consistent within their frameworks, and both would feel validated by the observations. This is where epistemology matters. How do we know what we know? Science relies on observation, measurement, and repeatability, while religion relies on revelation, scripture, and spiritual insight. When both point to the same event and say something significant is happening, but describe it with incompatible vocabularies, resolution becomes difficult. You cannot prove that spiritual entities do not use physical vessels to manifest. You cannot prove that advanced extraterrestrials are not misinterpreted as angels or demons. The frameworks are incommensurable in important ways. What we can say is that Bicker described a scenario using language from his religious tradition that overlaps significantly with scenarios described by scientists using secular language. Whether that overlap is the result of a shared underlying reality, from influence and informational cross-contamination, or from pure coincidence, does not change the sociological impact. Millions of people across religious and secular communities are now watching Atlas with rapt attention, expecting something dramatic. That expectation is critical. If nothing unusual happens, if the object completes its perihelion pass and continues on a purely gravitational trajectory, exhibiting normal cometary evolution, both communities will experience disappointment. The scientists who allowed themselves to consider the technological hypothesis will return to conventional explanations. The religious communities will adjust prophetic timelines, or reinterpret the vision as symbolic rather than literal. Life goes on, but if something does happen, if we observe deployments, maneuvers, transmissions, anything that scientifically confirms the mothership scenario, the religious interpretation will gain immense cultural power. Bigelow will have predicted not just one unlikely event, but two: the Trump assassination and the arrival of aliens. That feat would make him one of the most credible prophetic voices in modern history. Whether you accept his theological framework or not, you would have to concede that he somehow accessed accurate information about future events. The December observations will test this directly. If probes separate from Atlas and begin independent trajectories toward Earth or other planets, we will know within days. Telescopes, worldwide are positioned for the ISON campaign, specifically looking for this very sign. We will not go into October blindly. We will go in with the most comprehensive monitoring effort ever directed at an interstellar visitor. Bigelow's vision adds a narrative layer to that monitoring. He has given the observation human drama and visionary stakes, whether his interpretation is correct or not. He has ensured that when Atlas emerges from behind, the sun and astronomers report their findings. Those findings will be filtered through multiple simultaneous interpretive lenses. The story is no longer just scientific. It is cultural, spiritual, existential, and perhaps that is as it should be, if we are looking at something that challenges our understanding about our place in the universe, whether through technological contact or other means. It should engage more than just our scientific institutions. It should engage our spiritual traditions, our philosophical frameworks, our deepest questions about meaning and purpose. And the Atlas became a Rorschach inkblot test for the diverse ways humanity makes sense of the unknown. What we see in it says as much about us as it does about the object itself.